Hello everyone, welcome back. In this video, we're going to explore topic 5.1 using the mean value theorem and the row theorem. Alright, so the row theorem is the special case of the mean value theorem. Alright, so let's take a look at the mean value theorem. Then we're going to go back to the row theorem. Alright, now look at the picture on the right. In the figure to the right, label the indicated order pairs. So this guy A. This guy must be f of A, right? And this guy should be A. Now, the y coordinate of this one should be f of A, right? This guy is 17, B and f of B. And the y coordinate right here should be f of B. Alright, now label segment whose length is f of B minus f of A, which is right over run, right? So it could be from here to here. F of B minus f of A, right? In other words, it could be the distance from here to here, right? Now label a segment whose length is B minus A, which is this guy right here. B minus A, right? In other words, it's gonna be this guy, right? The quotient f of B minus f of A over B minus A actually right over run, right? This one is right and this one is run. Is the slope of the segment joining the 2 points A f of A and B f of B. F prime of C gives the slope of the line tangent to the curve of f s upon C fc. On the graph above, locate C values that's guaranteed by the mean value theorem and draw a line tangent to the curve at S equals C. So the red line right here is the tangent line to the curve. Now the two lines drawn on the graph of FOS are parallel to each other. Alright, so you look at this guy and this guy, they parallel. Thus, the conclusion of the mean value theorem can be restated as follows. There will be two parallel lines, one through the points A f of A and B f of B, and the other tangent to the curve f of S at the point C f of C, right? So the mean value theorem states if f is continuous on the closed interval A and B and differentiable on the open interval A and B, then there exists a number C inside the open interval A and B such that f prime of C equals f of B minus f of A over B minus A. So here's an extremely important information that you need to know. The function must be continuous on the closed interval A and B and differentiable on the open interval A and B. Right, the Rolle's theorem. Let f be a function that is continuous on the closed interval A and B and differentiable on the open interval A and B. If f of A equals f of B, then there is at least one number C in the open interval A and B such that f prime of C equals 0. Right? Why? Because we have, by the mean value theorem, it says f prime of C equals f of B minus f of A over B minus A. Now, since f of A equals f of B, so the numerator becomes 0, right? So 0 over B minus A is going to be 0. That's why you have this one, right? Now, look at example number 1, illustrating the Rolle's theorem. Determine if the Rolle's theorem applies 2, the function f of s equals s to the 4 minus 2s squared on the interval -2, 2. Alright, so first we're gonna check to see if the function f of s equals s to the 4 minus 2s squared continuous, right? So actually this is a polynomial function that should be continuous, right? And it's gonna be differentiable on the interval -2 and 2. Alright, I'm gonna calculate f of -2, right? So it's gonna be -2 to the 4 minus 2 times -2 squared equals 8, right? And f of 2 equals 2 to the 4 minus 2 times 2 squared, and it's gonna be 8, right? We have f prime of c equals 0, where c inside the open interval -2, 2. Now we need to solve for c, right? So we take the derivative of this one. So we have f prime of s equals 4s cubed minus 4s, right? Then f prime of c equals 4c cubed minus 4c, right? Now we let f prime of c equals 0. It's going to be the same thing as 4c cubed minus 4c equals 0, right? Factor 4c out, so it can be 4c times c squared minus 1, it becomes c minus 1 times c plus 1, right? Equals 0. So this one is the 0 product, right? So we have three values, c equals 0, c equals 1, and c equals -1. This guy right here is inside of this interval, right? So then there are three values that satisfy this row theorem, right? Now we're gonna sketch the graph so to see how it looks like, right? So it's gonna be something like this, and you have three values right here: f of 0, f of -1, and f of 1. They all equal 0, right? Let's take a look at example number 2, illustrating the mean value theorem. Determine if the mean value theorem applies to the function f of s equals 3 minus 5 over s on the interval 1, 5. State thoroughly the reason why or why not the theorem applies. If the theorem does apply, find the value of c, guarantee the theorem. Visually, what is the mean value theorem trying to find? Draw it in. Alright, so basically we need to check to see if the function is continuous and differentiable on the interval 1 and 5, right? On the interval 1 and 5, the function is continuous, right? Because the function is discontinuous right at s equals 0, right? But 0 is outside of this interval, right? So then you can say that the function f of s is continuous on the closed interval 1 and 5, right? And then the function f of s is also differentiable on the open interval 1 and 5, right? Now next, you need to take the first derivative of the function f of s. So it could be derivative of 3 equals 0, right? Derivative of 5 over s, it could be -5 over s squared. So combined with the negative side here, it becomes 5 over s squared, right? So then you have f prime of c equals 5 over c squared, right? Side note, you need to calculate f prime of c, that equals f of b minus f of a over b minus a, right? By the mean value theorem, right? So it's gonna be f of b, which means f of 5 minus f of 1 over 5 minus 1. F of 5, substitute 5 for s, the answer is 2, right? S equals 1, substitute 1 for s, so the answer is 2, right? Over 4, so the answer is 1, right? So then you need to equate this guy and this guy. F prime of c equals this, and f prime of c equals this, right? So we have 5 over c squared equals 1. Then you need to solve for c, right? So c equals plus and minus square root of 5, right? Now, you only pick one value. Why? Because within the interval 1 and 5, right? Negative root 5 is outside of this interval, right? So, you have c equals square root of 5 is inside the interval. So, c equals square root of 5 is the value that guarantees the mean value theorem, right? On the graph right here, you know that square root of 5 equals 2 point something, right? So give it somewhere right here, right? Alright, so the tangent line right at s equals square root of 5 is parallel to the second line within the interval 1 and 5, right? Now let's take a look at example number 3. Find the equation of the tangent line to the graph of f of s equals 2s plus sin s plus 1 on the interval 0 to pi at the point which is the solution to the mean value theorem, confirming using your graphing calculator. Alright, so first you need to find the first derivative of this function, right? So we have f prime of s equals 2 plus cosine s, right? So then you have f prime of c equals 2 plus cosine of c, right? Now you need to find f prime of c equals f of b minus f of a over b minus a by the mean value theorem, right? So b is pi, a is 0, right? So it turns out to be 2 pi plus sine pi plus 1, right? Minus 2 times 0 plus sine 0 plus 1, right? Over pi minus 0, right? Now sine pi equals 0, sine 0 equals 0, right? So the top becomes 2 pi plus 1 minus 1, right? Over pi. So it turns out to be 2, right? Now in order to apply the mean value theorem, this guy right here and this guy right here must be the same, right? So then cosine of c equals 0. Then c equals pi over 2 plus k pi, right? Now you need to find the solution within this interval only, right? So k should be equals 0, right? So then c must be equals pi over 2, right? Now you need to calculate the points, right? So f of c, which means f of pi over 2, and then you substitute pi over 2 for s into this equation right here, right? So you have 2 times pi over 2 plus sine pi over 2 plus 1, right? Now sine pi over 2 equals 1, right? And this guy cancel out, right? So it turns out to be pi plus 2, right? This one is the y value, right? The s value is right here, right? And then the slope is right here, right? So the equation should be y minus y1 equals m times s minus s1, right? Now it turns out to be y equals, the slope is 2 times s minus s1 right here, right? Minus pi over 2 plus y1 is going to be pi plus 2. This one is the equation of the tangent line. We're going to use the graphing calculator to check our work, right? So we're going to bring up the calculator. Alright, so we're going to add graphs. Alright, so the function is 2s plus sin s plus 1. And you hit enter. It's going to be something like this, right? And the tangent line should be right here. So you need to hit tab and you type the function right here, y equal 2 times s minus pi over 2 plus pi plus 2, right? Then you hit enter. So the function has the tangent line at s equal pi over 2 right here, right? Now I'm going to check to see if it's pi over 2, right? I hit menu, analyze graph right here, intersection, right? And move to the left, enter, move cursor to the right, hit enter. It's going to be right here, 1.571, which is pi over 2, right? Now let's move on to example number 4. When the mean value theorem does not apply. Explain precisely why we cannot apply the mean value theorem to either of the three functions below on the provided intervals. So we know that in order for the mean value theorem to apply, the function must be continuous on the closed interval and differentiable on the open interval, right? Alright, so we need to check this guy and this guy. Alright, so this one is the absolute value function, so it can be something like this, right? And of course the function is continuous, right? So this one satisfied, right? But the function is not differentiable, right, as square 3 right here, because it has a sharp turn, right? So the mean value theorem does not apply, right? Now let's move on to question B. G of s equals 2 over s plus 2 on the interval -3 and 1. Alright, so you see this one is the rational function, and then it's gonna have the vertical asymptote, right? So s plus 2 equals 0, and then s equals -2. This one is the vertical asymptote. That makes the function discontinuous at this point, right? So the mean value theorem does not apply, right? Now let's move on to question C. H of s equals s raised to the 2/3 on the interval -1, 3. Right? So we need to take derivative of this one to see what happens. So h prime of s equals, we're going to use the power rule, right? So it could be 2 over 3 s raised to the 2 over 3 minus 1. It could be -1 over 3, right? And then this guy turns out to be 2 over 3 times s raised to the 1 over 3, right? Now h prime of s is undefined when s equals 0, right? Which means the function is not differentiable as s equals 0, right? So then the mean value theorem does not apply. Now let's move on to example number 5. Real world application of the mean value theorem. Two stationary police cars equipped with radar are 5 miles apart on a highway, as seen in the figure right here, right? As you drive your sports car passes the first patrol car, your speed is clocked at 55 miles per hour. 4 minutes later, you pass the second patrol car who clocks you at 50 miles per hour. Is it possible that you could be issued a citation for exceeding the posted 55 miles per hour speed limit? Show your analysis. Alright, so we have the change in y and the change in s, right? So at t equals 0, I call this one as a, right? At t equals 4, I call this one as b, right? So I need to calculate the average velocity, right? By using the change in distance over change in time, which is f of b minus f of a over b minus a, right? Now f of b minus f of a equals 5 right here, right? So I have 5 over b minus a, which means 4 minus 0 is going to be 4 minutes, right? And this one is miles, right? Now the unit right here is miles per hour, so I need to convert this one to hours, right? So I need to multiply by 60 minutes over 1 hour, right? So it turns out to be 75 miles per hour, right? Now assume that the precision function is differentiable within this interval. So by the mean value theorem, you clearly traveling at more than 75 miles per hour at some moment, right? Therefore, you were in the speeding at some point during that interval, right? Now let's move on to example number 6. AB calculus BC 2003 question 83. Alright, the function f is continuous and differentiable on the closed interval 0, 4. The table above gives selected values for f on this interval. Which of the following statements must be true? A. The minimum values of f on the closed interval is 2. The maximum values of f on the closed interval is 4. f of s greater than 0 for s between 0 and 4. F prime of s less than 0 for s between 2 and 4. Alright, so for A, B, C, D right here, you're gonna learn it later, right? The answer actually is why there exists C within 0 and 4 for which F prime of C equals 0. We're gonna apply the Rolle's theorem, right? So the Rolle's theorem say F prime of C equals F of B minus F of A over B minus A equals 0, right? So let's check. Now within this interval we have this guy and this guy right here, right? So we have f prime of C equals, this one is A, this one is B, right? So we have 3 minus 3 over 3 minus 1 is going to be 0 over 2 is going to be 0. So this one is satisfied, right? So this one actually the special case of the mean value theorem. The answer must be E. Right. Now let's take a look at example number 7. AB calculus AB 2003 question 80. Suitable for BC. Alright, the function f is continuous on this interval and differentiable on this interval. If f of -2 equals -5, f of 1 equals 4. Which of the following statement could be false? Alright, so keep in mind we have the interval A, B. It's gonna be -2, 1, right? Then we have f of A equals -5, right? F of B equals 4, right? So we're going to use the mean value theorem, right? So we have f prime of C, where C inside this interval, right? Equals f of B minus f of A over B minus A. So it could be 4 minus -5 over 1 minus -2, right? So this guy turns out to be 9 over 3. So it could be 3, right? Different from 0, right? So the answer must be B, right? You could say false, right? Now let's move on to example number 8. AP calculus AB 1998 question 4. Alright, if the function f is continuous on the closed interval a and b and differentiable on the open interval a and b, which of the following could be false, right? So when we see the function is continuous and differentiable, think about the mean value theorem, right? Now question 8 right here. F prime of C equals f of B minus f of A over B minus A for some C such that C between A and B, yes, by mean value theorem, right? Now question B, f prime of C equals 0 for some C between A and B. No, it's not the case, right? This one is the special case of the mean value theorem, which is the Rolle's theorem, right? In this situation, f of A could be different from f of B, right? Look at the example number 7 right here. Is equal 3, not equals to 0, right? So this one is wrong, right? So this one should be the answer, right? You're gonna learn this one later. Now let's take a look at example number 9. AP calculus BC 2003 question 92. Let f be the function defined by f of s equal s plus natural log of s. What is the value of c for which the instantaneous rate of change of the function f s equals c is the same as the average rate of change of the function f over this interval, right? So, right, now since this one is the calculator active question, right? So we're gonna print up the calculator to check if the function is continuous and differentiable within the interval 1 and 4, right? I need to hit tab and put the function s plus natural log of s, and I hit enter. It's gonna be right here, right? Now I need to restrict the domain from 1 to 4, right? So I hit menu, Windows, zoom right here, Windows setting. S min should be 1, S max should be 4, right? I hit OK. It's gonna be right here, right? And you see that the function is continuous and differentiable within this interval, right? So the mean value theorem applied, right? So we have this one actually f prime of c, right? And this guy actually f of 4 minus f of 1 over 4 minus 1, right? So f of 4 is 4 plus natural log of 4 minus, substitute 1 for s, right? So it will be 1 plus natural log of 1, right? Over 3. And you need to simplify this one, so it's going to be natural log of 1 equals 0, right? So it could be 4 minus 1, it could be 3 plus natural log of 4 over 3, right? Now I'm going to bring up the calculator, right? Now I need to go to home screen, hit calculate, and put this one on the calculator, right? So it could be, convert this one to decimal, right? Menu, number, convert to decimal, hit enter. 1.4621. You need to solve for c, right? You need to calculate f prime of s. It's gonna be 1 plus 1 over s, right? This guy right here. Then f prime of c equals 1 plus 1 over c, right? So you need to equate this guy and this guy. So it could be 1 plus 1 over c equals 1.461, right? Now you need to solve for c, right? So 1 over c equals 0.461, right? So it could be c equals 1 divided by 0.461, right? So I'm going to bring up the calculator. It's going to be 1 divided by 0.461. Enter. The answer is 2.16403. 2.16403. The answer must be C, right? We're going to explore topic 5.2 Extreme Value Theorem, global versus local extrema and critical points. Now, extrema of a function. In calculus, we need to determine if the function f has a maximum value on the interval I. If the function f has a minimum value on the interval I. When the function f is increasing. When the function f is decreasing. Alright? So, throughout the unit, you will use the derivatives to answer this question, and more than apply them to real life situations. Alright? A function does not have to have a maximum or a minimum on an interval. For instance, in figure number 1, which is right here, you can see that the function f of s equals s squared plus 1 has both maximum and minimum on the closed interval -1 and 2. Right? This one is the maximum. This one is the minimum. Right? Now look at the figure number 2. You have no maximum, but you have minimum, right? It's gonna be right here because the function is continuous right here. But right here you see that this one is the whole, right? So the function is not defined by this one, right? So there is no maximum. Now look at the picture number 3. There is a maximum right here, but no minimum because the function is discontinuous right at this point, right? Now, the following theorem is a result from the situation to the left, the extreme value theorem. If the function f is continuous on a closed interval a and b, then the function f has both maximum and minimum on the interval, right? Now we're going to talk about the local, which means relative, or global, which means absolute, maxima, or minima. Among other local, relative, maxima, or minima, the greatest local or relative maximum is the global or absolute maximum, and the least local relative minimum is the global absolute minimum, right? Actually, you learn this one in AB pre-calculus, right? So we look at the following pictures right here. This guy has the local mass of -1 as s equal -4 and local mass of 2 when s equal 3, right? This guy also has the local mean of -4 as s equal -1, right? Now we need to find the absolute mass and mean, right? So look at this one. The greatest local mass is the global mass, right? So the greatest is right here. So this guy is the global mass, right? And the function has no absolute mean, right? Because this guy keep going forever, right? Now look at the picture number 2. The local mass is right here, -1 as s equal -5, and right here it's gonna be -1 as s equals 1, right? And the function has the local mean is gonna be right here, -5 as s equals -3, right? Now we're gonna talk about the global mass. The greatest local maximum is the absolute maximum, right? The greatest is -1 right here. So this one is the global mass, and the function does not have the global or absolute minimum, right? Now number 3, the local mass is right here, 3 as s equal -2, right? And this guy right here, -1 as s equal 4, right? Now the function has local minimums right here. It's gonna be -6 as s equal -5 and -3 as s equal 2, right? Now we're gonna check for the absolute maximum. Absolute maximum actually this guy right here, right? It's gonna be 3 as s equal -2, and absolute minimum is gonna be right here, right? -6 as s equal -5, right? Now let's move on to the next one, relative, extrema, and critical numbers. The graph of FOS equal SQ minus 3s squared to the right has a relative maximum, which is right here, right? And relative minimum, which is right here, right? To make this easier for you, think of the relative maximum as being a peak of a mountain on the graph, and the relative minimum occurring as the valley of the graph, right? Note that if these peaks and valleys have smooth rapid curves about them, then the graph has a horizontal tangent line at those points. Note that h is relative extrema. The derivative is either 0 or does not exist. The s values at these special points are called critical numbers. Definition of critical numbers. Let the function f be defined as a value c. If f prime of c equals 0, or if f is not differentiable at c, then c is called critical number of the function f. Definition of relative extrema. Let f be a function whose second derivative exists on an open interval I. If there is an open interval containing the value of c, on which f of c is a maximum, then f of c is called a relative maximum of the function f. If there is an open interval containing c, on which f of c is a minimum, then f of c is called a relative minimum of the function f. The plural of relative maximum is relative maxima, and the plural of the relative minimum is relative minima. Below are two examples of a critical number c of the function f. Now look at this one right here. The function has a sharp term, so f prime of c does not exist. Then c is a critical number of the function f. Now f prime of c equals 0 right here. The function has a horizontal tangent line, right? Relative extrema occur only at critical numbers. If the function f has a relative minimum or relative maximum at s equals c, then c is a critical number of the function f. Alright, now let's look at example number 1. If f is continuous on the closed interval a, b, and differentiable on the open interval a, b, which of the following could be false? A. F prime of c equals f of b minus f of a over b minus a for some c such that c between a and b. This one always choose by the mean value theorem, right? Now, answer choice B. F prime of c equals 0 for some c such that c between a and b. This is not always true, right? By the rho theorem, f a must be equals f of b, right? So this one is false. Question C and D. The function f has a minimum or maximum value on the closed interval a and b. This guy always choose by the extreme value theorem, which we just learned right here, right? It's right here. The final answer must be B, because it's a false. Now example number 2. The function f is defined on the closed interval 0 and 1 and satisfies f of 0 equals f of 1 half equals f of 1 on the open interval 0 and 1. F is continuous and strictly increasing. Which of the following statements is true? A. F attains both a minimum value and a maximum value on the closed interval 0 and 1. Question B. F attains a minimum value but not a maximum value on the closed interval 0, 1. Question C. F attains a maximum value but not a minimum value on the closed interval 0, 1. Question D. F attains neither a minimum value nor a maximum value on the closed interval 0 and 1. Alright, so go let's get this picture, right? So I have f of 0 equals f of 1 half equals f of 1, right? So it's going to be right here, and right here. This one is 0, 1 half, and 1, right? Now, on the open interval 0 and 1, which is from here to here, the function f is continuous and strictly increasing. Be careful, this one open interval 0 and 1, the function f is continuous and strictly increasing, right? So the function is undefined as 0 right here, right? and 1 right here. So it could be something like this. Right? Be careful. This one is closed interval. You have this guy. On the open interval, you have 2 holes right here. Right? So the function f is discontinuous on the closed interval 0 and 1. So if it's discontinuous, it doesn't have maximum nor minimum value, right? So the answer must be D. Now let's take a look at example number 3. Let g be a function given by g of s equal s squared times e to the ks, where k is a constant. For what values of k does the function g have a critical point s equal 3.5, right? So the first thing you need to do is to take derivative, right? I'm going to use the product rule, right? So remember u times v prime. It's going to be u prime v plus v prime u, right? So it's going to be 2s times e to the ks plus, now e to the ks is e to the u, right? Prime is going to be u prime times e to the u, right? So it turns out to be k times e to the ks times s squared, right? Now we know that the function f has a critical point s equal 3.5, right? So you have g prime of 3.5 right here must be equals to 0, right? So this guy is the same thing as substitute 3.5 for s into this guy right here. So have you just solve the equation for k, right? So this guy cancel out. So I'm gonna factor e raised to the 3.5 k out, right? So I have e raised to the 3.5 k. It's gonna be 3 plus 9 over 4 k equals 0. Now keep in mind this one always positive, right? So I don't need to worry about this guy, right? So I only need this guy to be 0, right? So I have 9 over 4k equals negative 3. K equals negative 12 over 9. Or k equals negative 4 over 3. So the answer must be A. We're going to explore the topic 5.3, determining intervals on which a function is increasing or decreasing. Alright, now first we're going to talk about the increasing and decreasing function. Definition of increasing and decreasing function. A function f is increasing on an interval if for any two numbers s1, s2 on the interval such that s1 less than s2. This implies that f of s1 less than f of s2, right? So you look at the right hand side right here, you see that the function is increasing on this interval right here, right? Because you're gonna take s1 here, right? And then s2 here, and observe that s1 less than s2. Then you see that f of s1 less than f of s2, right? A function f is decreasing on an interval if for any two numbers s1 and s2 on the interval such that s1 less than s2 implies that f of s1 greater than f of s2, and you see that the direction of this guy and this guy opposite, right? This guy and this guy have the same direction, so it's gonna be increasing. If they have opposite direction, it's gonna be decreasing, right? So we look at the right hand side. Now suppose I have s1 right here, right? s2 right here, and you see that s1 less than s2, right? But f of s2 less than f of s1. You see that, right? So you need to be careful, right? Now we're gonna talk about the theorem, the test for increasing and decreasing function. let f be a function that is continuous on the closed interval a and b, and differentiable on the open interval a and b. If f prime of s greater than 0 for all s in the open interval, then f is increasing on the closed interval a and b, right? Greater than 0 is going to be increasing. We talk about the f prime. Okay, keep that in mind. This guy different from this guy. This guy is the definition. We just talk about the function f of s. The theorem we talk about the function f prime of s. So you need to be careful. Number 2, if f prime of s less than 0 for all s in the interval a and b, then f is decreasing on this interval, right? So this less than is going to be decreasing. All right, so we look at the picture right here. This one is the function f of s, right? Now the interval from here to here, right? The function is decreasing. You see that? So within this interval, f prime of s less than 0. You see that? F prime of s less than 0, the function is decreasing, right? Now within this interval all the way to infinity, you see that? The function f of s is increasing, right? So f prime of s must be greater than 0. Why? You know that f prime of s is the slope of the tangent line, right? So you just draw the tangent line right here. It doesn't matter what tangent line you're going to draw, you always get the positive slope, right? Similarly, on the left hand side, it doesn't matter where you draw the tangent line, you still always get the negative slope, right? That's why f prime of s less than 0. Don't forget to use the Christmas tree trick, right? If the tangent line is going this way, slope is positive, right? If the slope is positive, the function is increasing, right? If the tangent line is going this way, the slope is negative. If the slope is negative, the function is decreasing, right? If the tangent line is going this way, which means the slope is 0. If the slope is 0, the function is constant, right? And if the tangent line is going this way, the slope is undefined, right? Now you look at this interval right here within a and b, it's going to be constant. Constant, which means the slope is 0. You see that? Alright, so keep that in mind. So you work on the increasing or decreasing function problem. You need to be careful with the graph of the function right here. The given graph f of s will be different from the given graph f prime of s. Alright, so you need to be careful. Now let's take a look at the first example. Given the function f prime of s, you see that? Alright, this guy different from this guy. This one given f of s. Alright, now intervals on which f is increasing or decreasing. The graph shown to the right is f prime of s. The derivative of f of s. Using the graph, find the critical values for f of s and study the intervals over which f of s is increasing, decreasing, and justify your answer. Alright, now we look at the right hand side right here. This is the graph of the function f prime of s. So in order to know if the function is increasing or decreasing, we need to check the sign of f prime of s, right? If it's greater than 0, less than 0, or equal to 0, right? So we need to find the 0 of the function f prime of s first, right? We have 3 zeros. The first one is right here, the second one is right here, and the third one right here, right? And you know that the function f prime of s is defined on the entire intervals, right? So we have the 0 f prime of s equals 0 when s equals 0, 2, and 4, right? Now we need to find the interval where the function is increasing or decreasing, right? So we look at the theorem right here. The function f is increasing on the interval a and b if f prime of s greater than 0, right? It's gonna be above the x-axis. Alright, so you need to look for the interval that's above the x-axis, right? It's gonna be this guy right here. right? And this guy right here above the x-axis, right? So the function f of s is increasing on the interval 0 to 2 and 4 to infinity, right? And the function f of s is decreasing on the interval negative infinity to 0 and 2 to 4, right? Because on this interval the function f prime of s is below the x-axis, right? Example number 2. Intervals on which f is increasing or decreasing. We need to use the first derivative, right? Find the intervals on which f of s is s cubed minus 3.5 s squared is increasing or decreasing, right? So we need to take the first derivative. It's going to be 3s squared minus 3s, right? And then you let the first derivative equals 0, right? So you have f prime of s equals 0. It's the same thing as 3s squared minus 3s equals 0, right? I'm going to factor 3s out, so it could be 3s times s minus 1 equals 0, right? This one is the 0 product, right? So s equals 0 and s equals 1, right? Now I need to use the side chart to check for the sign of f prime of s, right? Now in order to check for the sign of f prime of s, I need to test the number, right? So I pick a number 2 right here within the interval 1 to infinity, right? I substitute this guy back over here. I need to test to see if it's positive or negative, right? So I have 3 times 2 squared minus 3 times 2. It's going to be always positive, right? So this guy is positive. And you keep changing the sign, negative and positive, right? This way only correct if you have the 0 with odd multiplicity, right? If you have 0 with even multiplicity, it's going to be totally different, so be careful. Within this interval, the function is increasing because f prime of s is greater than 0, right? The function is increasing. This one, the function is increasing because f prime of s greater than 0, right? Within this interval, the function is decreasing because f prime of s less than 0, right? Here is the guidelines for finding intervals on which a function is increasing or decreasing. Let f be continuous on the interval a, b. To find the intervals on which f is increasing or decreasing, use the following step. First, locate the critical numbers, which is this one right here, right? Of f in the interval a and b, and use these numbers to determine your test intervals. Now, number 2, determine the sign of f prime of s by picking a test value in each of the intervals. Step number 3, use the theorem for increasing and decreasing function to determine whether the function increasing or decreasing. The guidelines above will also work if the interval a and b is replaced by an interval of the forms negative infinity to b, a to positive infinity, or negative infinity to positive infinity. Alright, and the last but not least, definition. A function is strictly monotonic on an interval if it's either increasing on the entire interval or decreasing on the entire interval. So you look at this one right here. This one is strictly increasing. This one is strictly decreasing. Right? The function is f of s equals s cubed. This one f of s equals negative s cubed. We'll explore topic 5.4 using the first derivative test to determine relative local extrema. Alright, we have new vocabularies. Extrema is the plural form of the extreme, meaning all maximum and minimum values. Minima is the plural form of the minimum. Maxima is the plural form of the maximum. Now, the first derivative. We have the theorem, the first derivative test. Let C be a critical number of the function f that is continuous on the open interval I. containing c. If the function f is differentiable on the interval except possibly as c, then f of c can be classified as follows. Number 1. If f prime of s changes from negative to positive as c, then f of c is a relative minimum of f. Alright, so you're going to sketch the diagram like this. Suppose the interval I is a and b, right? And c1, c2 inside the interval a and b. And suppose the function f prime of s changes sign from negative to positive as c1, which is the first one right here, right? I call this is c1 and f of c1, right? And from positive to negative as c2, which is the second case right here. Positive to negative as c2, and this one f of c2. Now, since f prime of s is negative, the function f of s is decreasing, right? And this one, the function f of s is increasing because f prime of s is positive right here, right? And similarly, this one is decreasing, right? So you have the relative minimum right here and relative maximum right here, right? Which is right here, right? Now, number 3, if f prime of s does not change the sign as c, f of c is neither a relative minimum nor relative maximum, right? You look at the picture right here, number 3 right here. The sign does not change. Look, f prime of s greater than 0 the first time, f prime of s greater than 0 for the second time, and it doesn't change sign at all. So neither relative minimum nor relative maximum in this situation. Or if it's negative, it's still negative right here. You see that? It's going down, and this guy going down, right? Remember the Christmas tree trick. If the tangent lines go this way, the slope is positive. Tangent lines go this way, slope is negative, right? Only the first two cases right here, the slope of the tangent lines change sign, right? Negative to positive, right? It could be like this. So this one is minimum. Positive to negative. This one is maximum. Now let's take a look at the first example. Apply the first derivative test. A. Find the points that are relative extrema of the function f of s equals 1/2 s minus sin s on the interval 0 to 2 pi. Alright, so what you need to do is to find the first derivative, right? So we have f prime of s is going to be 1/2 minus cosine s, right? And you let the first derivative equals 0, right? And it's going to be 1/2 minus cosine s equals 0, right? This guy is the same thing as cosine s equals 1/2, right? Now remember that the domain is from 0 to 2 pi, right? So this guy turns out to be s equals pi over 3 and 5 pi over 3, right? Now you're gonna sketch the diagram, right? So I'm gonna pick pi over 6 right here within this interval, right? I substitute pi over 6 for s into f prime right here, right? Because I need to check the sign of f prime of s, right? So this guy turns out to be 1/2 minus cosine of pi over 6 equals root 3 over 2, right? So observe that this guy always negative, right? So then this interval becomes negative, and you keep changing the sign. This one positive and this one negative, right? And the function decreasing within this interval, increasing within this interval, and decreasing within this interval, right? And right here you have the relative minimum and you have the relative maximum here, right? In order to find the points that are relative extrema, you need to substitute pi over 3 for s back to the original function right here, right? Because you need to find the value of f of s right here, right? So you have 1/2 times pi over 3 minus sine of pi over 3, right? So this guy turns out to be pi over 6 minus sine of pi over 3 equals root 3 over 2, right? I need to simplify this one, right? So this guy turns out to be pi subtract 3 root 3 over 6, right? So this guy turns out to be pi subtract 3 root 3 over 6. Now similarly, I need to substitute 5 pi over 3 for s into the function f of s right here, right? So I have 1/2 times 5 pi over 3 minus sine of 5 pi over 3, right? So it turns out to be 5 pi over 6. Sine of 5 pi over 3 equals negative root 3 over 2, and combined with the negative side right here, it becomes plus root 3 over 2, right? Now I need to simplify this guy. It turns out to be 5 pi plus 3 root 3 divided by 6, right? So this guy turns out to be 5 pi plus 3 root 3 divided by 6, right? Alright, now last but not least, you need to conclude, right? Now keep in mind, this table right here is the one that helps organize your thought. It's not the work you need to show on the AP exam, right? So on the AP exam, you need to write the function f of s has a relative minimum pi minus 3 root 3 over 6 at s equals pi over 3, because the function f prime of s changes from negative to positive at s equals pi over 3, right? Similarly, you need to say that the function f of s obtains the relative maximum 5 pi over 6 plus 3 root 3 over 6 at s equals 5 pi over 3, because the function f prime of s changes sign from positive to negative at s equals 5 pi over 3. Now let's move on to question B. Find the points that are relative extrema on the function f of s equal this one. Alright, first you need to calculate the first derivative, right? F of s. It turns out to be 2/3 times s squared minus 4 times 2s, right? You need to use the chain rule. U to the n prime equals n times u to the n minus 1 times u prime, right? So I'm going to simplify this guy. It turns out to be, oh, I forgot this one. 2/3 subtract 1 is going to be negative 1/3, right? So this guy turns out to be 4s over 3. I bring this one down to the bottom. It turns out to be cube root of s squared minus 4, right? You need to find the critical points. So in order to find the critical points of f prime of s, remember you learned before, it is where f prime of s equals 0 or undefined, right? Now if f prime of s equals 0, then 4s equals 0, right? So then s equals 0. If f prime of s is undefined, then the denominator equals 0, right? Which means s squared minus 4 equals 0. Then s equals plus and minus 2, right? Now you need to draw the diagram. Alright, so right at s equals 0, f prime of s equals 0, right? So you need to put a 0 right here. Right as s equals plus and minus 2, right? F prime of s is undefined, right? So you put 2 lines right here. Alright, now you're gonna check the sign, right? You're gonna pick a number within any intervals, right? So I'm gonna pick 1 right here. right? I substitute 1 for s back to f prime of s right here, right? I need to check for the sign, right? So I have 1 square minus 4 is going to be negative 3, right? So this guy becomes negative number, right? So within this interval it's going to be negative sign, right? Now you keep changing the sign. This one negative, this guy positive, this guy negative, this guy positive, and this guy negative. Or you're gonna test. If you pick 3, you substitute 3 for s over here. It's gonna be 9. 9 minus 4 is gonna be 5. It's positive, right? So this guy positive, this guy positive. Now if you pick negative 1 over here, right? So you substitute over here, negative 1 square is gonna be positive. Positive subtract 4 is going to be negative, right? Now negative multiplied by the negative number right here, it becomes positive. So that's why you have positive right here. And last one, you substitute negative 3, right? So it could be 9. 9 subtract 4 it could be positive. And this one is negative 6, so it becomes negative, right? Now, if f prime of s is negative, the function is decreasing. This one, f prime of s is positive, the function is increasing. This one, function is decreasing. And this one, function is increasing, right? And you have the relative minimum right here, relative maximum here, and relative minimum right here, right? And you substitute negative 2 for s back to the original function right here to solve for f of s right here, right? So I have negative 2, substitute over here, it's going to be 4, 4 subtract 4, it's going to be 0, so this guy equals 0, right? Similarly, 2 is equals 0, right? Now, relative maximum, you need to substitute 0 for s, right? It's going to be 0 square minus 4 raised to the 2/3, right? So it could be negative 4 altogether raised to the 2/3, right? So it's going to be cube root of negative 4 square, right? So it could be cube root of 16, right? So right here you have cube root of 16. Alright, now you can give a conclusion easily, right? Based on the diagram right here, you can say that f of s has a relative minimum of 0 at s equal negative 2 and 2, right? Because f prime of s changes sign from negative to positive at s equal negative 2 and 2. Now, similarly, the function f of s has a relative maximum of cube root of 16 at s equals 0, because the function f prime of s changes sign from positive to negative at s equals 0. Now let's move on to question C. Find the points that are relative extrema of the function f of s. Now we need to find the first derivative, right? So f prime of s equals, we need to use the quotient rule, right? So it could be u over v prime. It's going to be u prime v minus v prime u over v squared, right? So this guy turns out to be 4s cubed times s squared minus 2s times s to the 4 plus 1 over s to the 4, right? I'm going to simplify this one. It's going to be 4s to the 5th minus 2s to the 5th minus 2s, right? Over s to the 4. So this guy turns out to be 2s to the 5th minus 2s over s to the 4. I need to divide the top and bottom by s. So this guy turns out to be 2s to the 4 minus 2 over s cubed, right? Now I need to find critical numbers, right? Remember, critical numbers is where f prime of s is undefined or equals 0, right? Now f prime of s equals 0 when the numerator equals 0, right? So it could be 2s to the 4 minus 2 equals 0. If you solve this one, s equals plus and minus 1, right? Now f prime of s is undefined when s q equals 0, then s equals 0, right? Again, you're gonna sketch the diagram, right? Alright, so f prime of s equals 0 when s equals plus and minus 1, right? So this one equals 0, this one equals 0. Look, f prime of s right here, right? Now f prime of s is undefined when s equals 0, right? So you're gonna put 2 lines right here. Alright, now you're gonna test the interval, right? So within this interval, I'm gonna pick 2, right? I substitute 2 for s into f prime of s, which is right here, right? So I have 2 times 2 to the 4 minus 2 over 2 cubed. This is always positive, right? So this one positive. Then you keep changing the sign, right? So it could be negative, positive, and negative. This guy negative, the function is decreasing. This guy positive, the function is increasing. This guy negative, the function is decreasing. And this guy positive, the function is increasing, right? So based on the diagram, you have the relative minimum right here, right? This guy relative minimum right here. Now a lot of students could make some mistake right here, because they're gonna say the function f prime of s changes sign from positive to negative as s were 0. So the function f of s obtains the maximum, right? But when you substitute 0 for s back to the original function right here, observe that the function is undefined, right? So this guy is undefined. Therefore, there is no relative maximum right here. You only have 2 relative minima. That's it, right? Now, to find the relative minimum, substitute -1 for s back to the original function right here, f of s, right? Because you need to solve for f of s, right? So -1 to the 4 is going to be 1, 1 plus 1 is going to be 2, 2 over 1 is going to be 2, right? Similarly, this one should be 2, right? So you need to conclude that the function f of s has a relative minimum at -1, 2, and 1, 2, because f prime of s changes sign from negative to positive at s equals -1 and s equals 1, right? And there is no relative maximum because the function f of s is undefined at s equals 0. Now we can bring up the calculator to check our work, right? So we're gonna go to question A right here. Now you need to add graphs, right? So you need to input the function right here, 1/2 s minus s, right? And you hit enter, it's gonna be right here. Now you need to restrict the domain, right? Domain is should be 0 to 2 pi, right? So you need to hit menu number 4 right here and number 1, right? S min should be 0, right? S max should be 2 pi, right? Which means 6.28. You hit OK, it's gonna be right here, right? Now you have one relative minimum, right? And one relative maximum, right? It's gonna be right here. Now I'm gonna hit menu, analyze graph, minimum here, right? And move to the left, to the right. It's gonna be right here, right? Relative minimum. Now similarly, I need to find the relative maximum. I need to hit menu, number, set, relative, maximum. Move my vertical line to the left, to the right. The answer is right here, right? Now for question B, I need to hit Control I, add graphs. I need to input s squared minus 4 raised to the 2/3, right? And hit enter. You have two relative minima right here, right? So you need to hit menu, number, set, and minimum. Move to the left, move to the right. It's gonna be right here, right? And similarly, menu, number, set, minimum, move to the left, move to the right, and it's gonna be right here. You need to find the relative maximum. It's gonna be right here, right? So menu, analyze graph, maximum, move to the left, move to the right. It's gonna be right here, right? Now let's move on to question C. Alright, I'm gonna hit Control I, add graphs. I'm gonna input the function. Hit enter. It's gonna be right here. Now observe that the function does not have relative maximum, right? Because it keeps going forever. You see that? You only have two relative minima right here, right? So you need to hit menu, number, set, minimum, move to the left, move to the right. The first relative minimum. Now similarly, menu, number, set, number 2, move to the left, move to the right. The second relative minimum, right? We're going to explore topic 5.5 using the candidate test to determine absolute or global extrema. Now, finding absolute extrema on a closed interval. Step number 1, find the critical numbers of f in the open interval a and b. Step number 2, evaluate f as its critical number in the open interval. Step number 3, evaluate f as each endpoint of the closed interval a and b. Note that these two steps are referred to as the candidate test. Now, step number 4, make a conclusion. The list of these f values is the absolute minimum or global minimum. The greatest is the absolute or global maximum, right? Note that the actual maximum or minimum value is y value, where the maximum or minimum occurs would be an s value, right? Now example number 1. Find the absolute extrema on a closed interval. Question A. Find the absolute extrema of the function f of x equals 3s to the 4 minus 4s cubed on the interval -1 to 2. So first you need to find the first derivative, right? It's gonna be 12s cubed minus 12s squared. And then you need to find critical numbers by letting f prime of s equals 0, right? So it turns out to be 12s cubed minus 12s squared equals 0. Factor 12s squared out. It's going to be s minus 1 equals 0. And then you have s equals 0. This one is multiplicity of 2, right? And s equals 1. We're going to start the table. Alright, now you need to place the values of this interval on the table, right? So it can be -1 and 2, right? Then the critical numbers right here, 0 and 1, right? So 0, 1. Alright, f of -1, substitute -1 for s into this function right here. It turns out to be 7, right? Substitute 0 for s back into this function right here. It's gonna be 0. Substitute 1, it turns out to be -1. And substitute 2, it turns out to be 16, right? Now we look at this one right here. Step number 4. The list of these f values is the absolute minimum. and the greatest is the absolute maximum, right? So you just conclude that the function f of s has an absolute maximum of 16 at s equal 2 and absolute minimum of -1 at s equal 1. We're going to use the calculator to check our work, right? Bring up the calculator and graphs right here. Input the function, right? Then hit enter. It's going to be right here. Now you need to restrict the domain to -1 and 2, right? So you're going to hit menu, Windows settings right here. Should be -1 and 2 for s value. And hit enter. It's going to be right here. Alright, so now you need to hit menu, analyze graph, minimum, right? You have the absolute minimum right here, the lowest one, right? Hit enter, go to right, hit enter, the answer right here, -1, which is right here, right? Let's move on to question B. Find the extrema of this function on the closed interval -1 and 3. Now you do exactly the same thing, right? You need to find f prime of s. It's going to be 2 minus 3 times 2/3 is going to be 2. S power 2/3 subtract 1 is going to be -1/3. So this guy turns out to be 2 minus 2 over cube root of s, right? Now let f prime of s equal 0. So that you're going to find the critical number, right? So this guy turns out to be, it's going to be 2 over cube root of s equals 2, right? Then cube root of s equals 2 divided by 2, it's going to be 1, right? And you're going to cube both sides, so it turns out to be s equal 1, right? Numbers occur when f prime of s is equal to 0 or undefined, right? So you need to write f prime of s is undefined when s equal 0, right? Look at this one right here. S equal 0, f prime of s is undefined, right? So you need to conclude that the candidate should be 0, 1, and -1 and 3, right? Now you're going to skip the table. Now you substitute -1 for s back to the original function. It's going to be right here. 2 times -1 minus 3 times -1 power 2/3. It's going to be -2 minus 3 is going to be -5. So the answer right here should be -5. Now s equal 0 is going to be 0. S equal 1 is going to be -1. And s equal 3 is going to be 2 times 3 equals 6 minus 3 cube root of 3 square is going to be 9, right? So you have 6 minus 3 cube root of 9. Now if you use a calculator to check, this guy right here must be less than 0, right? So then you need to conclude that f of s has an absolute maximum of 0 at s equal 0, right? And an absolute minimum of -5 at s equal -1, right? Now you can use the calculator to check your work, right? So you need to hit Control I, add graphs, input the function right here, 2s minus 3 times s to the 2/3. Hit enter, it's going to be right here. Now you need to restrict the domain, right, from -1 to 3. So you need to hit menu, window setting right here, -1, 3. Hit enter, it's going to be right here. Alright, so absolute maximum is 0 at s equal 0, right? And absolute minimum is on the left hand side right here, -5 right here at s equal -1, right? Now let's move on to question C. Find the extrema of f of s equals 2 sin s minus cosine 2s on this interval, right? So you need to take the first derivative. F prime of s is going to be 2 cosine s. Now this guy right here, you need to apply the formula cosine u prime is going to be negative u prime times sine u, right? Chain rule. So u in this situation is 2s, right? So 2s prime is going to be 2, right? So it's going to be negative 2 times sine of 2s, right? Now don't forget the negative side right here, so it becomes positive, right? So you need to let f prime of s equals 0 to find critical numbers, right? You know that sine 2s equals 2 sine s cosine s, right? So it could be 2 cosine s plus 2 sine s cosine s equals 0, right? And 2 right here, it becomes 4, right? Alright, now I'm going to factor 2 cosine s out. So it could be 1 plus 2 sine s equals 0, right? Now this one is the 0 product, right? So each of this one should be equals 0, right? So I have 2 cosine s equals 0. Then cosine s equals 0, and then s equals pi over 2 and 3 pi over 2, right? Look at the domain right here, 0 to 2 pi. Alright, 1 plus 2 sine s equals 0. Then sine s equals negative 1/2, right? So s equals 7 pi over 6 and 11 pi over 6, right? Now you have the candidates. It's going to be 0 and 2 pi, right? So 0 go first. Next one should be what? Pi over 2. Next 3 pi over 2. Next 7 pi over 6. Next 11 pi over 6. And the last one 2 pi, right? Now you need to sketch a table. Substitute these values back into the original function right here. Alright, so we have sine of 0 equals 0, cosine of 0 equals 1, so it will be negative 1, right? Now pi over 2, sine of pi over 2 equals 1, so you have 2 times 1. Cosine of 2 times pi over 2, which means cosine of pi equals negative 1, and negative side right here becomes positive, right? So plus 1, it's going to be 3, right? Now next, sine of 3 pi over 2 equals negative 1, right? So you have 2 times negative 1. Cosine of 2 times 3 pi over 2, it could be cosine of 3 pi, which is negative 1, and negative 1 right here becomes positive, right? So it could be negative 1. Alright, now the absolute maximum is 3 as s squared pi over 2, and the absolute minimum is negative 3.5 as s equals pi over 6 and 11 pi over 6, right? Now the graph for question A, B, C is right here, right? Now let's move on to example number 2. Find the minimum and maximum velocity and acceleration. Alright, a particle moves along a straight line with s of t equal this one for t within 0 and 3. Find the minimum and maximum velocity of the particles on the interval 0 and 3. Alright, now you need to take the first derivative of this one, right? So I have v of t equals s prime of t. It's going to be 4t cubed minus 12t squared plus 12t, right? Then in order to find the minimum and maximum velocity, you need to take the second derivative of this one, or the first derivative of vt, right? So this guy turns out to be 12t squared minus 24t plus 12, right? Let the v prime of t equals 0 is the same thing as 12t squared minus 24t plus 12 equals 0, right? So I'm going to divide both sides by 12. It turns out to be t squared minus 2t plus 1 equals 0, right? So it's going to be a complete square, right? So it could be t minus 1 all together square equals 0. So it's going to be t minus 1 equals to 0, right? And then t equals 1, right? This one is the first candidate, right? Now you have the second candidate right here, 0, and the third candidate is going to be 3, right? So you're going to sketch the table. Now substitute t equals 0 into the function v of t right here, right? It's going to be 0, right? Now t equals 1, it's going to be 4 minus 12 plus 12, it's going to be 4, right? And t equals 3, it's going to be 36, right? Alright, so you're going to say that the maximum velocity of the particle is 36 at t equals 3, right? And the minimum velocity of the particle is 0 at t equals 0, right? You can conclude this one, right? Exactly the same thing. Now, question B, the minimum and maximum acceleration of the particle, right? So you have the first derivative of velocity is the acceleration function, right? So I copy this one down over here. Now, in order to find the minimum and maximum, I need to take derivative of this one. So I have a prime of t equals 24t minus 24, right? I need to find critical number, right? So a prime of t equals 0, right? And then 24t minus 24 equals 0 and t equals 1, right? This one is the first candidate. And don't forget the second candidate and third candidate right here, right? So you're going to sketch the table, right? Substitute 0 for t into the function a of t, which is right here. It's going to be 12. And then t for 1 is going to be 0. T for 3 is going to be 48. Now you can conclude that the maximum acceleration of the particles is 48 at t equals 3, right? And the minimum acceleration of the particle is 0 at t equals 1, right? We're going to explore the topic 5.6, determining concavity of functions over their domains. Alright, concavity. Consider the following function f of x equals 1 over s minus 1. Alright, so if we use the graphing calculator, we graph it, it's going to be something like this. This one is the rational function. Alright, so as you learn in AP pre-calculus, the graph of f is concave down. Right here, right? Which means from negative infinity to 1, right? Where 1 is the vertical asymptote. And concave up is going to be from 1 to positive infinity, right? Keep in mind, if the graph looks like this, or half of this one, like this, the function is concave up, right? Or it looks like this, or half of that, something like this, is concave down, right? Definition of concavity. Let f be a differentiable function on an open interval I. The graph of f is concave upward on the interval I. If f prime of s is increasing on the interval and concave downward on the interval I, if f prime of f is decreasing on that interval, right? Now, test for concavity. Let f be a function whose second derivative exists on an open interval a, b. If f double prime of s greater than 0 for all s in the open interval a, b, then the graph of f is concave upward on that interval, right? If f double prime of s less than 0 for all s in the open interval a, b, then the graph of f is concave downward on the open interval a, b, right? Definition of a point of inflection. A point of inflection is an order pair where graph changes concavity, right? So which means if it changes from concave downward to upward, or upward to downward like this, right? So the point of inflection is to be somewhere right here, right? Now the point of inflection theorem. If C f of C is a point of inflection of the graph of f, then either f the program of s equals 0 or f is not differentiable at s equals c. Alright, let's take a look at the first example. Determine the open intervals on which each graph is concave upward or downward, and say any points of inflection justify your answer. Question A. f of s equals f to the 4 minus 4s cubed. You need to take the first derivative and second derivative, right? So I have first derivative f of s equals 4s cubed minus 12s squared, right? And the second derivative is going to be 12s squared minus 24s, right? Now you need to let the second derivative equals to 0, right? So you have 12s squared minus 24s equal to 0. And then you need to solve for s, right? So I have 12s, factor this one out, so it could be s minus 2 equal to 0. So then I have s equals 0, right? And s equals 2, right? Now I need to create a side charge, right? Negative infinity to positive infinity, right? Now I have two values right here, 0 and 2, right? I need to place 0 here and 2 here, right? Now I need to check the sign for f the program of s, right? So I need to pick a number within any intervals, right? So for example, I'm going to pick number 1 right here, right? Within the interval 0, 2, right? Substitute 1 for s back to the second derivative function right here. So then I have what? 12 minus 24, which is negative, right? So this guy is negative. Now you keep changing the sign because the 0 right here, they all have multiplicity, right? So you just change this one to positive, this one positive, right? Now go back to the theorem right here. The theorem says if f the program of s greater than 0 on the interval a and b, the graph of f is concave upward, right? If f the program of s less than 0, the graph is concave downward, right? So I need to say that the function f of s is concave upward from negative infinity to 0 and from 2 to positive infinity, right? And concave downward from 0 to 2, right? And the function f of s has a point of inflection at s equals 0 and s equals 2, right? Because f the program of s changes sign as these two values, right? If you use the graphing calculator to graph this function and identify the point of inflection or concavity, it should be something like this right here, right? Now let's move on to question B. f of s equals 6 over s squared plus 3. Now you do exactly the same thing, right? Now I need to rewrite f of s as 6 times s squared plus 3 power of negative 1, right? So I'm going to use the power rules, right? So I have f prime of s is going to be negative 6 times s squared plus 3 power of negative 2, right? And then times 2s, right? You need to use the formula u power of n prime is to be n times u power of n minus 1 times u prime, right? So this guy turns out to be 2s, right? And it's going to be negative 12s times s plus 3 raised to the negative 2, right? You need to calculate the second derivative, right? So you need to use the product rule, right? So it could be u times v prime. It could be u prime v plus v prime u, right? So this guy turns out to be negative 12 times s squared plus 3 raised to the negative 2 plus v prime is to be negative 2 to the front, right? Negative 2 and negative 12s becomes 24s, right? Times 2s and then times s squared plus 3 power negative 3, right? Now I need to combine this guy and this guy. 24 times 2 is to be 48 and s times s to be s squared, right? So this one turns out to be 48s squared. Now I need to bring this one to fraction, right? So it could be negative 12 over s squared plus 3 squared plus 48 s squared over s squared plus 3 power 3, right? Now I need to rewrite this one in the same denominator, so I need to multiply the first one by s squared plus 3, right? So it turns out to be negative 12 times s squared plus 3 plus 48 s squared over s squared plus 3 all together cubed, right? Now I need to simplify the top, so I distribute negative 12, right? So it turns out to be negative 12 s squared, right? And negative 12 times 3 is to be negative 36, right? Alright, now I need to simplify 48 subtract 12 is to be 36, right? So this guy turns out to be 36s squared. Alright, now I need to find the zeros of second derivative, right? So this guy turns out to be f the program of s equals 0 is the same thing as 36s squared minus 36 equals 0. If you solve this one, s equals plus and minus 1, right? Now you need to find the value of s where f the program of s undefined, right? This guy undefined when denominator is 0, right? So you need to write f the program of s is undefined when s squared plus 3 equals 0, right? But this one always greater than 0, right? So there's no value of s, right? You're gonna create a side chart, negative 1 and 1, right? F the program of s always defined, right? So which means negative infinity to positive infinity, right? This guy are 2 0 of the f the program of s, right? Now you're gonna test value, so I'm gonna pick a number 2 right here. I substitute this guy into f the program of s, right? Which is right here. Then I'm gonna have a positive side, right? This guy positive, this guy should be negative, right? And this guy should be positive, right? So within the interval negative infinity to negative 1, the function LOS concave up, right? This guy concave up, and this interval concave down, right? And the function LOS has two inflection points at s equal negative 1 and 1, right? Because f the program of s changes sign as these two values, right? And if you graph it, it's going to be something like this. Now let's move on to question C. We need to calculate the first derivative of f of s, right? And we need to use the quotient rule, right? So u over v prime is going to be u prime v minus v prime u, over b squared, right? So this guy turns out to be 2s times s squared minus 4, right? Minus 2s times s squared plus 1 over s squared minus 4 all together square. Now I need to simplify this one, so it will be 2s cubed, right? Minus 8s minus 2s cubed minus 2s, right? Over s squared minus 4 all together square, right? The numerator becomes negative 10s over s squared minus 4 all together square, right? Now second derivative is going to be quotient rule again, right? So it will be negative 10 times s squared minus 4 all together square, right? Minus over s squared minus 4 all together power 4, right? Now I need to simplify this one. Negative 2s times 2 is going to be negative 4s times negative 10s is going to be plus 40s squared, right? So I have 40s squared right here. Now I need to factor s squared minus 4 out, right? So I have s squared minus 4 times negative 10 times s squared minus 4, right? Plus 40s squared, right? Over s squared minus 4 all together power 4, right? Now this guy cancel out. Now I need to distribute this guy, right? So the numerator becomes 40s squared subtract 10s squared, it could be 30s squared, right? Negative 10 times negative 4 is going to be plus 40, right? Over s squared minus 4 power 3, right? Now I need to let f the program of s equals 0 is the same thing as 30s squared plus 40 equals 0, right? This equation has no solution, right? Because 30s squared plus 40 always greater than 0, right? Now you need to find the value of s squared at the program of s undefined, right? So f the program of s is undefined when denominator equal to 0, which is s squared minus 4 equal to 0, right? And then s equals plus and minus 2, right? Alright, now you need to put this guy on the number line, right? So you have negative 2 right here, 2 right here. Now you need to check the sign of f the program of s, right? So here's f the program of s. Alright. Now you're going to pick a value, right? So I'm going to pick a 0 right here. I substitute into f the program of s right here. The top is positive, the bottom is negative, right? Because 0 squared equals 0 minus 4 is going to be negative 4 power 3. It's going to be negative, right? So this interval is negative. Then you keep changing the sign, positive e and positive e, right? Or you can pick a number right here. For example, I pick number 3. I substitute over here. It's going to be positive, right? I pick a negative 3 right here. I substitute over here. It's going to be positive, right? So you can conclude that f(x) is concave upward on the interval negative infinity to negative 2, right? And to positive infinity seen at the program of s greater than 0 on those intervals, right? Now f(x) is concave that work on the interval negative 2 and 2 seen at the program of s less than 0 on that interval, right? Now f(x) has no points of inflection, right? Because f the program of s equals 0 has no solution. Now if you graph the third function, it looks like this, right? Now let's move on to the next example. Let f be a function such that f the program of s less than 0 for all s in the closed interval 2 and 3, which selected values of f of s shown in the table below. Which of the following must be true about f prime of 2.5? Alright, now since f the program of s less than 0, it tells us that the function f of s is differentiable and continuous, right? And also f prime of s is decreasing, right? So we're going to use the mean value theorem, right? So the mean value theorem say if the function f of s is continuous on the closed interval a and b and differentiable on the open interval a and b, then you have f prime of c equals f of b minus f of a over b minus a, where c inside the interval a and b, right? So I'm gonna pick this interval 2.3 and 2.5, right? So I have the value of c between this interval. So I have f prime of c equals f of b, which means 4.38, right? Subtract f of a, which means 4.12, over b minus a, which is 2.5, subtract 2.3, right? And this guy turns out to be 0.26 divided by 0.2. It's going to be 1.3, right? Now, since the function f prime of s is decreasing, it tells us that if you have s1, s2, then f prime of s1 must be less than f prime of s2, right? So I'm gonna have c less than 2.5, right? Then f prime of c must be greater than f prime of 2.5, right? F prime of c is 1.3, right? So I have f prime of 2.5 less than 1.3, right? Now similarly, I'm going to apply the mean value theorem one more time. This time I'm going to pick the interval 2.5 and 2.7, right? So I have the value of c between 2.5 and 2.7, right? So f prime of c is f of 2.7, which is 4.6 minus 4.38 over 2.7 subtract 2.5. Alright, so it turns out to be 0.22 divided by 0.2. It's going to be 1.1, right? Now, since f prime of s is decreasing function, right? So if you have c greater than 2.5, right? This one right here, then f prime of c must be less than f prime of 2.5, right? But f prime of c is 1.1, right? So I have 1.1 less than f prime of 2.5, right? Now I need to combine this guy and this guy. So finally I have 1.1 less than f prime of 2.5 less than 1.3, right? And the answer must be C. We're going to explore the topic 5.7 using the second derivative test to determine extrema. Alright, we're going to talk about the second derivative test theorem. Let f be a function such that f prime of c equals 0, which is c is a critical number, and the second derivative of f exists on an open interval containing c. If f the program of c is greater than 0, it tells us that the function is concave up. It's going to be like this, right? Then f of c is a relative minimum, right? You have relative minimum right here, right? Now, if f the program of c less than 0, which is the function concave down, then you have the relative maximum, which is right here, right? F of C is a relative maximum. Now, if f the program of C equals 0, then the second derivative test is inconclusive. There may or may not be a relative extrema as S squared C. You may have to use the first derivative test to determine relative extrema. Alright, let's take a look at the first example. Find the relative extrema for f of s equals negative 3s to the fifth plus 5s cubed using the second derivative test. Alright, so we have f prime of s is negative 15s to the 4 plus 15s squared, right? Then you need to find critical points. So you have f prime of s equals 0. Then you have negative 15s to the 4 plus 15s squared equals 0, right? Now I'm going to factor 15s squared out. So it can be negative s squared plus 1 equals 0. Alright, so you're going to solve this one. It's going to be s equals 0. S equals plus and minus 1, right? Now you need to find f of 0. It's going to be substitute 0 back to the original function right here, right? So I have 0, right? Now f of 1, I'm going to have negative 3 plus 5 is going to be 2, and f of negative 1 is going to be 3 minus 5 is going to be negative 2, right? Now you need to calculate the second derivative test. It's going to be 4 times negative 15 is going to be negative 60 s cubed plus 30 s, right? Now I'm going to check f the program of 0. It's going to be 0, right? F the program of 1 is going to be negative 60 plus 30 is going to be negative 30, right? F the program of negative 1 is 30. By the second derivative test, we have this guy less than 0, which means the function concave down, right? Then you have the relative maximum right here, right? The value of relative maximum is s equals 1 and y equals 2, right? So you have the point 1, 2 is the relative maximum. Now this guy greater than 0, then the function is concave up, right? Then you have the relative minimum, and the value of relative minimum is s equals negative 1, y equals negative 2 right here, right? And at the program of 0 equals 0, this one is inconclusive, right? You see that the relative minimum is right here, relative maximum is here, right? Now let's move on to example number 2. Given the values below for s, f of s, f prime of s, and f the program of s, along with the fact that f of s has only 2 zeros on the interval negative 3, 10, right? So you look at this one, the first 0 is right here, the second 0 is right here, right? And f the program of s has only 1 0 on the interval negative 3, 10. This one is the only 1 0 right here for f the program of s, right here. Now answer each of the following question. Question A. Identify all s values where f has a relative minimum. Justify using the first derivative test. Right? So you know that if s equals c is a relative minimum, then f prime of c must be equal to 0, right? And f prime of c must change sign from negative to positive, right? It's gonna be like this. So this one is relative minimum, right? So we look at the table, we're gonna pick the values that matches this information right here, right? So you have two zeros right here, -1 and 3, right? Which is this and this. Now we look at the side changes for f prime of s, right? From negative to positive, which is right here, -1 to 2, right? So s equal 3 is a value at which the function f has a relative minimum, right? Because f prime of 3 equals 0 and f prime of s changes sign from negative to positive, right? Alright, let's move on to question B. Identify all s values where f has a relative maximum. Justify using the second derivative test. Alright, so f has a relative maximum as s equals -1 right here, because f prime of -1 equals 0 and f double prime of -1 equals -1, which is negative, right? So then the function is concave down, right? Then it has a relative maximum here, right? Right, let's move on to question C. Identify all s values where f has a point of inflection. Justify your answer. Alright, so f of s has a point of inflection where f double prime of s equal to 0 and f double prime of s changes sign from negative to positive or positive to negative at that point, right? So we look at this one right here, f double prime of s equal to 0 when s equals 1, right? Right here. And f double prime of s changes sign from negative to positive, right? Alright, let's move on to question D. What is the equation of the tangent line to the curve y equal f of s at s equal 5? Alright, remember y minus y1 equals m times s minus s1 is the equation of the tangent line to the curve, right? Now we need to find s1, y1 first, right? So s equal 5 right here is s1, right? And then we need to find y1, right? Substitute 5 for s back to the original function, which is the table right here. S equal 5, y equals 3 right here, right? So y1 equals 3. Alright, so we finish y1, s1. We need the slope, right? The slope right here actually f prime of 5, right? Now we need to find f prime of 5. F prime right here, f prime of 5 equals 2, right? So we have f prime of 5 equals 2, and the equation should be y minus y1 equals m, which means 2 times s minus s1, which is 5, right? And then I'm going to add y1 both sides, so to be plus 3, right? And then if you want to simplify, go ahead do it. If you don't want it, just leave it, right? So I'm going to simplify it to be 2s minus 7, right? Now let's move on to the last question. Now this question is good for you to practice prior to the topics 5.8 and 5.9. The function f of s is a choice differentiable function with selected values of f, f prime, and f double prime given in the table below, right? At which s values does f of s have a relative maximum? Explain your reasoning. Alright, so this problem raises a question. Should we use the first derivative test or the second derivative test in this situation? Alright, so observe that the problem does not state that the only critical values of f prime of s occurs as s equals 5 and 2, right? It doesn't say anything, right? It's different from the previous question. The previous question say f prime of s has only 2 zeros on this interval, right? Only 2. This one doesn't say anything, right? So in this situation, the first derivative test is not a good choice, right? We would have to use the second derivative test, right? Now, the function f(s) has a relative maximum at s for phi y because you have f prime of phi equals 0, right? And f double prime of phi less than 0, right? It tells us that the function concave down, right? And it has the relative maximum right here, right? So by the second derivative test, we can conclude that s equals phi is the value at which the function f(s) has a relative maximum. And we're going to explore topic 5.8 and 5.9. Relationship between the function, the first derivative and the second derivative. Alright, first we're going to graph the derivative function f prime given the function f, right? Now, this one is the quadratic function, right? So for example, if you have y equals 2s squared plus 3s plus 1, alright? And then you're going to take the derivative of this one, it turns out to be 4s plus 3, right? So this guy turns out to be linear, right? So you see that this is the quadratic function. Then the first derivative should be the linear function, right? It's match this one, right? So how do we graph this one? Alright, so you look at this one right here. The relative extrema of the parabola becomes the 0 of the first derivative, right? Now next one, you're gonna draw the tangent line on the left hand side of the relative extrema right here, and you see that the slope of the tangent line is negative, right? So when you graph it on the graph of the function f prime of s, it is below the x-axis, right? On the right hand side, you draw the tangent line and you see that the slope is positive, so it should be above the x-axis, right? Now here's the Christmas tree trick. If the tangent line is going this way, the slope is positive. Tangent line is going this way, slope is negative. Tangent line is going this way, slope is 0. Tangent line is going this way, slope is undefined. Alright. Now the second one, this one is the cubic function, right? So for example, I have y equals 3s or 3 plus 2s squared plus s plus 1. Alright. Now if I take the derivative of this one, it's going to be what? 9s squared plus 4s plus 1, right? So it becomes quadratic, right? So this one, you see that when you take the derivative, it becomes the quadratic function, right? Now, how do we graph this one? We look at this one right here. The relative extrema of the original function becomes a 0 of the first derivative function, right? So it could be 0 right here, right? Next one. This one is the inflection point. All inflection points become the relative extrema of the first derivative function. Now we're going to check this one first, right? So from here to here, we're going to draw the tangent line. We see that the slope of the tangent line is positive, so it should be above the axis, right? From negative infinity to this guy, right? Now draw another tangent line. You see that from here to here, it should be negative, right? The slope is negative, it should be below the axis, right? Now from here to here, when you draw a tangent line, it should be negative, right? So it should be below the axis. Then the point of inflection right here becomes a local minimum of f prime of s, right? Now next one, we draw the tangent line of this one. We see that the slope is positive, so it should be above the axis, right? Now let's move on to the last one. This is the quadratic function, right? We're gonna locate the relative extrema of this function, right? It's gonna be right here. It's gonna be right here, and it's gonna be right here. So we have 2 minima and 1 maximum, right? So all relative extrema becomes the 0 of the function of f prime of s, right? So we just project out 0 right here, 0 right here, and 0 right here, right? Now this guy and this guy are inflection points, right? So it's gonna be relative extrema of the function f prime of s, right? So I draw the tangent line and see that the tangent line is going down, the slope is negative, so this guy should be below the axis, right? Next one, from here to here, draw the tangent line. It's gonna be positive, right? So it's gonna be above the axis, above, right? And then this one, keep doing that, draw a tangent line. The slope is gonna be positive, right? So it should be above the axis, right? So it could be like this, right? And then the inflection point right here becomes the maximum, right? Similarly, I'm gonna draw the tangent line right here. I see that the slope is negative, right? So it should be below the axis, right? Similarly, this guy, the slope is negative, it should be below the axis. Then the point of inflection right here becomes minimum value, right? And then the last one, I'm gonna draw the tangent line of this guy. The slope should be positive, right? Then it should be above the axis for the function f prime of s, right? Alright, what do you notice about each pair? Now, if the slope of the tangent line of f of s is negative, right? Look, the slope of the tangent line is negative. Then the graph of f prime of s will be below the axis, right? Below right here. If the slope of the tangent line of the function f of s is positive, right? This guy is positive. Then the graph of f prime of s will be above the axis. Look, it's above the axis, right? Now, all relative extrema of f of s will become x-intercept of f prime of s, right? Look, you have the minimum, this guy becomes the 0 of f of s, right? Maximum and minimum becomes the 0 of f prime of s, right? Minimum, maximum, minimum becomes the 0 right here, right? Now next one, all points of inflection of f of s will become relative extrema of f prime of s, right? So you see that the point of inflection right here becomes the minimum, right? The point of inflection right here becomes the maximum. The point of inflection right here becomes the minimum, right? Now, if f of s is an odd function, then f prime of s is an even function. The converse is not necessarily true. If f of s is an even function, then f prime of s is an odd function. Similarly, the converse is not always true. Now, let's move on to the first example. Sketch the function of the f prime of f given the function f of s. Right? Now, this one is the absolute value function. Right? First, we need to find the slope of the tangent line. Right? This one is the linear from here to here. The slope of the tangent line is -1, right? So it's gonna be -1 right here, right? From negative infinity to 2, right? Now remember that this one is the sharp turn, and you learned before at the sharp turn the function is not differentiable, right? So right here you should have the hole, right? Next one, from 2 to positive infinity, the slope is 2, right? So it's gonna be right here, the hole right here, and it's gonna be like this. This one is the graph of the function f prime of s, right? Now let's move on to example number 2. Given the parabola, we need to sketch f prime of s, right? This one is f of s. Alright, we need to locate the relative extrema, right? The relative extrema becomes the 0 of the function f prime of s, right? So it's gonna be right, s equal to y equals 4, right? So the 0 is right here. Alright, next one, you need to draw the tangent line on the left of 2, right? So it could be like this. And you see that the slope of the tangent line is positive, right? Which means it's going to be above the axis, right? So it could be something like this. Now, second one, we need to draw the tangent line right here. And you see that the slope is negative, right? Which means the second half should be below the axis, so it could be something like this. And this one is the graph of the function f prime of x, right? Now let's move on to example number 3. First, you need to locate the minimum and maximum, right? This one is the minimum, this one is the maximum. Minimum and maximum become 0 of the function f prime of x, right? So it could be 0 and 2, right? So 0 here and 2 here. Now the point of inflection is right here at 1, right? This guy becomes relative extrema of this one, right? So it could be right here. Now from negative infinity to 0, we need to draw the tangent line of the function f of x. And you see that the slope of the tangent line is negative, right? Which means the graph of f prime of x should be below the axis, right? So it could be something like this. Next, we need to draw the tangent line from here. And the slope is positive, right? So this guy should be above the axis, right? So it could be like this. Next one, we draw the net tangent line. And this one is positive, right? It's still above the axis. And the last one, draw the tangent line, it should be negative, right? So it should be below the axis, something like that. Now let's move on to example number 4. Alright, so we just draw the tangent line of this guy, right? And we see that the slope of the tangent line is getting smaller and smaller, right? But it's positive, right? So the graph of the function f prime of x should be above the axis, right? So it's gonna be something like this. Alright, now example number 5, sketch the function f prime of x given the 4-degree function. Alright, so first we need to locate the minimum, maximum, and the point of inflection, right? So we have the minimum right here, and we have the point of inflection right here. The minimum becomes the 0, right? So I have the 0 should be somewhere right here, right? And the point of inflection becomes the maximum or minimum, right? Right at 0, so it could be right here, right? Now I'm going to draw the tangent line. The slope of the tangent line is negative, right? From negative infinity to 0, right? Which means it's below the axis, right? So it could be like this. Now from 0 to 2, I'm going to draw the tangent line. And I see that the slope of the tangent line is negative, right? So it should be below the axis, so it could be something like this, right? And then from 2 all the way to close to 4 right here. Right? And I'm going to draw another tangent line. I see that the slope of the tangent line is negative, right? So it's still below the axis, right? So it could be something like this. And then from close to 4 all the way to positive infinity, the slope of the tangent line is positive, right? So it should be above the axis, so it should be something like this. Now let's move on to example number 6. From negative infinity to negative 2, you see that the slope is 0, right? So it should be on the x-axis, right? And then you see that right at the sharp turn right here, the function is not differentiable, right? So I'm going to draw the horizontal line on the x-axis from negative infinity to negative 2, right? And right here it should be the open circle because it's going to be undefined, right? Now from negative 2 to negative 1, you will see that the slope is positive, right? The slope is positive and it's going to be equal to 2, right? So the slope equals 2 from negative 2 to negative 1. So it's going to be right here. the slope equal to, so it's going to be like this. Again, right at this point, the function is not differentiable because it had a sharp turn, right? Now, from -1 to 1, right? It's going to be right here, the slope is 0, right? So it's going to be on the x-axis, right? So -1 right here to 1 right here, the slope is 0, so it should be like this. And then this one is the minimum, this one is the maximum, right? So it becomes the 0 of the derivative function, right? So it could be 2 as right here. I have 1, 0, and right here roughly 4, right? So it could be something like this, right? 2, 0. And then the point of inflection is right here at 3, right? So it becomes maximum, right? So I leave it over there. Now I'm going to draw the tangent line right here. I see that the slope of the tangent line is negative, right? From 1 to 2. So from 1 to 2, the slope is negative, the function below the axis, right? And remember, right at this point, the function is not differentiable, right? Because this has a sharp turn, right? So it's going to be, now I'm going to draw another tangent line right here. And I see that the slope of the tangent line is positive, right? From 2 to 3, right? It should be above the axis, right? Now the point of inflection is at s equals 3, right? So this point becomes the maximum of the function f prime of s, so it could be something like this. Now I will draw another tangent line. I see that it's positive, right? So it's still above the axis, so it could be like this. And I draw another tangent line. It's going to be negative, right? So this guy should be below the axis. Now let's move on to example number 7. Alright, given the function sine s, right? So now we need to locate the minimum and maximum, right? So minimum right here and maximum right here. They become the 0, right? So it could be right here and right here. Alright, and the point of inflection right here become the maximum, right? So it could be somewhere right here. Now I need to draw the tangent line of this guy, and I know that the slope of tangent line is negative, right? So it should be below the axis, right? So it could be something like this. From here to here, the slope is positive, right? So it's going to be above the axis, right? So it could be like this. From -1.5 to 0, right? -1.5 to 0. And then from 0 to 1.5 right here, the slope is positive, so it could be above the axis, so it could be like this. Now from 1.5 all the way to infinity, the slope is negative, right? So it could be below the axis, so it could be something like this, right? Now we can use the graphing calculator to check out work, right? So we're gonna bring up the calculator, hit add graph right here. Now function f1, we need to put sine s, right? Hit trick sine s and hit enter. It's gonna be like this, right? Now I'm gonna restrict the domain so that it looks like this one, right? So I'm gonna hit menu, window, zoom, and then window setting right here. So as mean, I'm gonna put -4. As mass, I'm gonna put 4. Y min should be -2, and Y mass should be 2, right? Enter. It's gonna be something like this. All right. Now I need to grab the function f prime of this guy, right? So I need to hit tab, and then I need to hit this button right here that's next to number 9, right? I'm gonna hit this one, derivative right here, right? Now I need to take derivative of the function sine s with respect to s, right? So I need to hit f1 of s, right? Then I hit enter. And you observe that the minimum of the original function becomes the 0 of the derivative function, right? The maximum right here becomes the 0 right here. You see that? The point of inflection right here becomes the maximum. It matches this guy. You see that? Now I just find the minimum, maximum, and the point of inflection, and I'm gonna match this guy to see how it looks like, right? So I hit menu, analyze graph, the minimum, right? Minimum of this guy, right? So I need to move cursor to the left, to the right. It's gonna be right here, right? Now I need to find the 0 of this guy, right? So I need to hit menu, analyze graph, 0, right? Move my cursor to the left of 0, move to the right of 0, and you see that this guy and this guy are the same. You see that? Negative 1.57, negative 1.57, right? They're both the same, right? Similarly, you will get this guy and this guy the same. This guy and this guy the same. This guy and this guy the same, right? Now, let's move on to the last one. Sketch the graph of the rational function. Observe that this one is the rational function and it's going to be undefined at s for -4 because -4 is the vertical asymptote, right? So when you turn this one into the derivative function, it's not differentiable at s for -4, right? Now you're going to draw the tangent line and you see that the tangent line is getting steeper, right? Which means it's going to be positive, right? So it's going to be above that axis, so it could be something like this. Alright, similarly, you're going to draw the tangent line of this guy and you see that the tangent line getting less steep, right? And the slope is still positive, right? So it could be like this. Let's use the calculator to check this one. This guy actually f of s equals. So we're gonna bring up the calculator. We're gonna sketch the function f of s equal s plus 2 over s plus 4. And then you hit enter. It's gonna be like this, right? So now you hit tab. f2 of s is derivative of f1 of s, right? So you hit this guy right here with respect to s. Right here, you just type f1s, right? And you hit enter. It's gonna be like this. See that? It matches this guy right here, right? We're gonna explore the topic 5.8, 5.9, part B. Reconstruct the function f from the function f prime. Now, in order to do that, you need to understand the following. If f prime of s greater than 0, then the function f of s is increasing, right? It's gonna be like this. If f prime of s less than 0, the function f of s is decreasing, right? Now, if f prime of s changes from negative to positive, right? Negative, which means going down, positive going up, right? So right here you have the relative minimum, right? If f prime of s changes from positive to negative, right? Which means going up and then going down, you have the relative maximum right here, right? Now f prime of s is increasing, then f of s is concave upward, because if f prime of s is increasing, f double prime of s must be greater than 0. The function f of s is concave up, right? Now similarly, f prime of s is decreasing, which means f double prime of s less than 0, right? It tells us that f of s is concave backward, right? F prime of s has an extremum, then f of s has a point of inflection, right? Look at this one right here. Relative maximum, relative minimum of the function f prime of s. These two guys become the point of inflection right here, right? Now the 0 of f prime of s, 1, 2, 3, become the minimum, maximum, and minimum, right? How do we know which one is the minimum, which one is the maximum? we look at this one right here. And this guy right here. Alright, if f prime of x changes from negative to positive, right? Look at this one right here. This guy below the x-axis, right? Of the function f prime of s, so it can be negative, right? And then this guy above the x-axis is going to be positive, right? So it changes from negative to positive, right? Which means it's going down first and going up like this. So this is minimum, right? Similarly, this guy right here above the axis, so it can be positive. This guy right here below the axis, so it can be negative, right? So the side change from positive to negative, which means going up first, going down. This is maximum, right? So this guy becomes maximum, right? And the last one right here, this guy below the axis, so it can be negative. This guy above the axis, it's going to be positive, right? So it changes from negative to positive. It's going to be like this, right? So it can be minimum. We need to draw the tangent line. And we see that the tangent line is going up, which means the slope of the tangent line is positive. So the slope of the tangent line of f prime of s is f double prime of s, right? So which means f double prime of s is positive. And this guy positive, the function is concave up, right? Similarly, you just draw the tangent line right here, right? You see that the slope of this tangent line is negative, right? Which means f double prime of s less than 0. The function is concave downward, right? And the last one, this one is concave upward, right? Right here. Now let's look at example number 9. Given f prime of s, we need to sketch f of s, right? Now f prime of s is right here. This guy, right? This is straight line y equals 2, right? It tells us that this one is the slope of the function f of s, right? The slope of the function f of s is 2, right? So we just find the slope right here and we connect it. So this one is the function of f of s, right? It's actually the linear function. Now we just make up an example, right? So y equals 2s plus 2 or something like that. If we take the derivative of this one, it turns out to be 2, right? So it's going to be 2 right here. You see that? You can do backwards, you will see it. Now, what if f prime of s is right here? Does that mean f prime of s is 0 everywhere, right? Then when you sketch the function f of s, it's going to be either like this, or like this, right? Because when you take the derivative of this one, for example, I have y equals 4. This is y equals negative 4. This is y equals 0. When you take the derivative of this guy, it's going to be 0. Y prime equals 0, right? So, since f prime is 0 everywhere, the slope of f is 0 everywhere. So f must be a constant. Below are the possible graph of f of s, right? We have 3 different cases: positive constant, 0, or negative constant, right? Now let's move on to question B. The function f prime of s is a linear function, right? Then the possible f of s must be a quadratic function, right? Now we need to locate the 0 right here, right? The 0 of f prime of s becomes the minimum or maximum of f of s, right? Now we need to look at this one right here, this guy below the axis, right? So it's going to be less than 0, right? F prime of s less than 0. It tells us that the function f of s is decreasing, right? So it could be like this, right? And this guy right here is above the axis, right? It tells us that f prime of s is greater than 0. Then the function f of s must be increasing, right? So it could be like this. Then this guy right here becomes the minimum of f of s, right? Now let's move on to question C. Alright, so we observe that the function f prime of s always below the axis, right? It tells us that f prime of s always less than 0 or equal to 0, right? On the interval negative infinity to positive infinity, right? And then it tells us that the function f of s always decreasing, right? Now we need to locate this one. This one is the maximum of the f prime of s. It becomes the point of inflection of the function f of s, right? So it could be right here. Now again, look at this one. This one is parabola, which means quadratic, right? When you scale the function f of s, is actually the cubic function, right? So now this one in the interval negative infinity to 0. F the program of s is positive, right? You just draw the tangent line, right? And the slope is positive. It tells us that f the program of s is positive, right? If this one positive, it tells us that the function f of s from negative infinity to 0 is concave upward, right? So it's gonna be something like this. And on the right side, you just draw the tangent line and you see that f the program of s is less than 0, right? The slope of this one is negative, right? And then f of s must be concave downward, right? So it could be like this. Now let's move on to question D. First, we need to locate the 0 of the function f prime of s, right? So we have negative 4, negative 2, and 4, right? So this 0 becomes the relative extrema of the function f of s, right? So we know that the function f of s must pass the point negative 4 and 2, right? So I'm going to locate the negative 4 and 2, the point right here, right? That's the first point. Alright, and we know that from negative infinity to negative 4, the function f prime of s is less than 0, right? So because this is below the axis, right? So the function f of s should be decreasing, right? And this guy right here actually the relative minimum because f prime of s changes sign from negative to positive right here, right? So you know that negative to positive is going to be relative minimum, right? So it could be decreasing like this. Alright, now next one. From negative 4 to negative 3, f prime of s is above the axis, so it could be increasing, right? So this guy going up, right? Now keep in mind, right at negative 3, this guy is the relative extrema of f prime of s, then it becomes the point of inflection of the function f of s, right? From here, you just draw the tangent line. You see that the slope of the tangent line of f prime of s is positive, which means the f the program of s right here is positive. The function is concave up. Similarly, this one f the program of s is negative. The function is concave down, right? So the point of inflection right at negative 3, so concave up and concave down is going to be something like this. Alright, now next one right at negative 2. F prime of s is above the axis from here to here. Do you see that? And then below the axis from here to here. So it changes sign from positive to negative. Positive to negative is going to be maximum here, right? So right here is going to be maximum here, right? So it's going down like this, right? Next one we have one right here. This one is the relative minimum of f prime of s. This guy becomes the point of inflection of f of s, right? So right here it should have the point of inflection right here. And right at over here, this one changes sign from negative to positive. Negative to positive is actually the minimum, right? So it's gonna be something like this, right? Right at 4 right here, this one is the minimum. Then from 4 to positive infinity, the function f prime of s is above the axis. So the function f of s is to be increasing, right? So to be like this. So finally, we're going to check our work. The relative minimum right here, relative minimum right here, relative maximum. The point of inflection is here, right? Point of inflection is here. Now we check our work. Point of inflection is 1 and -3, which is correct, right? The 0 right here become the relative extrema, right? Minimum, maximum, and minimum, right? Now let's move on to question E. We need to locate the relative extrema and point of inflection, right? So we see that the 0 of f prime of s right here becomes the relative extrema of the function f of s, right? So it could be somewhere right here or right here, right? Depend. Now you have the relative extrema right here and relative extrema right here. These two guys right here becomes the point of inflection, right? So -3 should be somewhere right here and 1 should be somewhere right here. Now observe that the function f prime of s is below the axis from -infinity to -5, right? So from -infinity to -5, the function f of s is decreasing, right? So it could be something like this. As for -5, the function obtains the relative minimum, right? Because it changes sign from negative to positive, right? Negative to positive is to be minimum. Alright, so it's going up right here, right? From -5 to -3, f prime of s is above the axis, so it could be increasing, right? From -3 to -1 right here, f prime of s above the axis, so it keep increasing, right? But if you draw the f double prime of s, right, it's gonna be negative. It tells us that the function f of s is concave downward, right? So it's gonna be like this. And you have the point of inflection is at -3, right? The minimum value is at s equal -5, right? From -1 to 1, you draw the tangent line. You see that f double prime of s less than 0, right? So it will be concave downward, right? So it's gonna be something like this. Now right at 1, this one is the point of inflection, right? From 1 to positive infinity, f double prime of s is positive. The function concave upward, right? So it could be something like this. Alright, so finally you have the point of inflection is right here and right here, right? -3 and 1. The relative minimum is at s equal -5, right? And the function f of s is decreasing from -infinity to -5, right? Increasing from -5 all the way to positive infinity, right? Now observe that the function f of s is concave upward from -infinity to -3, right? We look at this one, -infinity to -3. F double prime of s is positive, right? And from 1 to positive infinity, right? Look at this one, f double prime of s is positive, right? And concave downward from -3 all the way to 1, right? So this one right here, concave downward. Now let's move on to question F. You see that the 0, -1, right? And the function f prime of s changes sign from negative to positive, right? Because this section right here below the axis so it could be negative, and this section right here above the axis so it could be positive, right? So when it changes the sign from negative to positive, which means the function f of s decreasing and increasing, right? And this one is should be relative minimum, right? So at s equal negative 1 is going to be relative minimum right here, right? Now, from negative infinity to negative 1 right here, f prime of s is negative, the function f of s is decreasing, so it's going to be something like this. From negative 1 to positive infinity, the function f prime of s above the axis, so it's going to be positive, right? The function f of s is increasing, right? And observe that if you draw the tangent line right here, so does that mean f double prime of s positive, right? Similarly, you're going to draw the tangent line right here, f double prime of s still positive, right? Which means the function f of s is concave up on negative infinity to positive infinity, right? Now let's move on to question G. First, we need to locate the 0 of f prime of s, so it's going to be negative 4 and 3, right? And the function f prime of s changes sign from negative to positive, right? Because it's below the axis right here and this one above the axis, right? So negative, positive, and then this guy right here from positive to negative, right? So this guy becomes the relative minimum, this guy becomes the relative maximum, right? So max as 3 and minimum as negative 4, right? So negative 4 right here, this one minimum and this one is maximum, right? So it could be something like this, right? Now, from negative infinity to negative 4, the function f of s is decreasing because f prime of s below the axis is going to be negative, right? So this guy decreasing. Alright, and then from 3 to positive infinity, it's going to be decreasing, right? So it could be something like this. Now from negative 4 to 3, f prime of s above the axis, so it could be greater than 0, right? So f of s should be increasing, right? And then the point of inflection is right here because this is relative estimate of the function f prime of s, right? So we have the point of inflection at s equal 1, right? So I need to lower down this one, negative 4, the minimum should be somewhere right here, right? From negative infinity to 1. The function f of s is concave upward because if you draw the tangent line, you see that f double prime of s always positive, right? So this guy should be concave upward from negative infinity to 1. So it could be something like this, right? And then from 1 all the way to positive infinity, the slope of the tangent line right here should be negative, right? So the function f of s should be concave downward, right? It's going to be something like this. The minimum value is right here. The maximum is here. The point of inflection is here. The function increasing from negative 4 to 3, right? So negative 4 to 3. The function is decreasing from negative infinity to negative 4 and 3 to positive infinity, right? Now let's move on to question H. At s equal 1, this one is the 0 of f prime of s and it becomes the relative estimate of the function f of s, right? And we see that the function f prime of s changes sign from positive to negative, right? So positive to negative. This one is the relative maximum of the function f of s, right? So at s equal 1 is the relative maximum right here. Now, f prime of x is positive from negative infinity to 1, right? Which means the function f of x is increasing, right? So it's going to be something like this. And negative from 1 to positive, infinitive, right? So it could be decreasing. Now we're going to check the second derivative, draw the tangent line, and we see that the slope of the tangent line is negative, which means f prime of s always less than 0. From negative infinitive to positive infinitive, it tells us that the function f of s always concave downward on the entire domain, right? And there is no point of inflection, right? Now let's move on to question I. The function f prime of s has 2, 0 right here. This guy becomes extrema of the function f of s, right? Observe that this guy is positive because it's above the axis, and this guy is negative because it's below the axis, right? The function is increasing and decreasing, so this one is maximum, right? So at 1 the function obtains the maximum value, right? And similarly at 3 this one is negative, this one is positive, right? So this one is positive, it's going up, this guy is minimum, right? So minimum is 3 right here. Now you see that the function f prime of s has the vertical asymptote, which means f of s is not differentiable on this point, right? So right here I just draw the vertical asymptote as s squared 2, which means the function f of s is not defined as s squared 2, right? Now since this one is above the axis, which means f prime of s is positive, it tells us that the function f of s is increasing, right? From negative infinity to 1, right? So negative infinity to 1, so it could be like this, right? And decreasing from 1 to 2, right? So from 1 to 2 it's going to be decreasing, so it could be like this, right? So this one is the maximum. Now you just draw the tangent line right here, and you see that the slope of the tangent line is negative. It tells us that f double prime of s is negative. So f of s is concave downward, right? Alright, now similarly, from negative 2 to 3, the function f prime of s is below the axis, right? So it tells us that the function f of s is decreasing on this interval, right? So it's going to be something like this. And from 3 to positive infinity, the function f prime of s is above the axis. It tells us that f prime of s is greater than 0. Then the function f of s is increasing on this interval. So it could be something like this, right? And observe that this one is the relative minimum, right? Now you just draw the tangent line, you will see that the slope of the tangent line always positive, right? It tells us that f double prime of s greater than 0. Then the function f of s is concave upward, right? Like this. Now let's move on to question J. We know that f prime of s is greater than 0 from negative infinity to positive infinity, right? It's set as s squared negative 2. And then the function f of s is increasing on the real number, right? Now f double prime of s is less than 0 from negative infinity to negative 2. It tells us that the function f of s is concave downward on this interval, right? Similarly, the function f of s is concave upward from negative 2 to positive infinity, right? Because f double prime of s is positive, right? Now f of s has no relative maximum nor minimum, right? Because this one is positive, this one is still positive, it's all above the axis, right? But f of s has a point of inflection as s squared negative 2 because this one is concave downward, right? and this one is concave upward, so it could be like this, right? So we have the point of inflection s for -2, so it could be somewhere over here, right? Now from -infinity to -2, the function f prime of s is above the axis, so the function f of s should be increasing, right? So it could be something like this. And from -2 to positive infinity, it's still increasing, right? So it could be like this. Now let's move on to example number 10. Sketch a possible f of s with the following characteristic. Alright, question A. F prime of s greater than 0. This one tells us that the function f of s is increasing, right? For all s, so it's going to be on the entire domain, right? F double prime of s greater than 0 tells us that the function f of s is concave upward, right? Now f1 equals -2, so s for 1 y equals -2 is going to be right here, right? Function f of s should be something like this. F prime of s greater than 0 for s greater than 1. It tells us that the function f of s is increasing on the interval 1 to infinity. And f prime of s less than 0 for s less than 1. It tells us that the function f of s is decreasing on the interval -infinity to 1, right? Now f prime of 1 equals 0. This one is the 0 of the function f prime of s. This guy becomes the relative extrema of the function f of s, right? Now f double prime of s greater than 0 for all s. It tells us that the function f of s always concave up, right? And f of 1 equals -1, right? F of 1 equals -1 is going to be right here, right? So f prime of s greater than 0 for s greater than 1. So it's going to be something like this. Alright, f prime of s less than 0 for s less than 1. It's going to be something like this, right? F prime of 1 equals 0. So this guy becomes the relative minimum, right? Because the function f of s always concave up, right? Now question C. F prime of s greater than 0 for s greater than 2. It tells us that the function f of s is increasing on this interval, right? And f prime of s equals 0 for s less than or equal to 2. It tells us that the function f of s will be a constant on this interval, right? And f double prime of s greater than 0 for s greater than 2. The function is always concave on this interval, right? And f of 2 equals 1. F of 2 equals 1, so to be right here, right? And it's to be something like this. This one should be a straight line, and this one should be a curve. Alright, let's move on to question D. F prime of s greater than 0 for s greater than -1. So the function f of s should be increasing on this interval, right? And f prime of s less than 0 for s less than -1. The function f should be decreasing on this interval, right? Now, this is important. F double prime of s less than 0 for all s different from -1. So this guy tells us that the function f of s always concave there, right? And f of -1 equals -2. So it could be something like this. Now let's move on to question E. First, we need to locate the relative extrema, right? So the 0 of the function f prime of s become the relative extrema, right? Now we have -3 and 1, right? So we need to look at this one here, f prime of s greater than 0 when s less than -3, right? So it could be positive right here and less than 0 from -3 to 1. So this guy becomes maximum, right? So -3 should be somewhere right here, right? And 1 right here becomes the minimum, right? Because f prime of s greater than 0 for s greater than 1, right? So minimum should be somewhere right here. Now next one, f of 0 equals 0, so the function must pass the origin, right? Now we know that f the parameter s less than 0 for s less than -1, right? So from here all the way to the left, the function fs is concave backward, right? From here all the way to the right, the function fs concave upward, right? So we just get a graph is something like this. So we see that from -infinity to -1, right? The function fs is concave backward, and from -1 to positive infinity, the function fs is concave upward, right? And we have the relative maximum right here, relative minimum is right here. The function fs passes the origin, right? Now let's move on to the last question. Question f. F prime of s greater than 0 for s greater than 2. F prime of s equal -1/2 for s less than 2. F prime of 2 does not exist. F double prime of s less than 0 for s greater than 2, and f of 2 equals 0. So f of 2 equals 0, which means the function passes this guy, right? And we know that f prime of s equal -1/2 for s less than 2. It tells us that the function f of s should be a linear function on this interval, right? So it should be something like this, -1/2 s plus 2, something like that, right? For s less than 2. I'm going to locate the y-intercept, right? Y-intercept equals 2, right? So I'm going to go down by 1, go to the right by 2, right? So it could be something like this. This is a straight line, right? Now, f prime of s greater than 0 for s greater than 2. It tells us that the function f of s is increasing on this interval, right? And f prime of 2 does not exist. It tells us that the function f of s has a sharp turn right here, right? F double prime of s less than 0 for s greater than 2. It tells us that within this interval, the function is concave backward, right? So it could be something like this. We're going to explore topic 5.10 and 5.11, optimization problems. Alright, one of the most common applications of calculus involves the determination of minimum and maximum values. Consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum sign, least sign, greatest strength, or greatest distance. Before outlining a general problem-solving strategies for such problems, let's look at an example. Alright, example number 1. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimension should the box be in order to produce a box with a maximum volume? Alright, so we have two things to consider. The first one is primary equation. Primary equation is what the question asks you to do, which is the maximum volume, right? And the second one is the secondary equation, which is what's given, right? So it's given 108 right here, right? So you have the primary equation is the volume of the box, right? So this is a rectangular prism, right? So the volume should be length times width times height, right? So V equals this guy, same, right? So it could be s squared times height right here. Now the secondary equation is the surface area of the rectangular prism, which means you're gonna add the area of all faces up, right? Because this one is an open box, right? So we don't count the top, right? Now from this secondary equation, we're gonna solve for h, and then we're gonna substitute that one into the primary equation, right? So I have h equals 108 subtract s squared over 4s, right? Alright, so the primary equation becomes v equals s squared times 108 minus s squared over 4s. The goal is we just create an equation with one variable, right? Previously, this equation contains two variables, right? Now we're going to simplify this one, so this guy turns out to be v equals. Now we're going to take the derivative of this one, so v prime equals 27 minus 3 4s squared, right? We let this one equal to 0, right? We solve for s, so I have s squared equals 36, then s equals 6. Now we have two values right here, it's going to be plus and minus 6, right? Since the side length of the open box right here should be positive, right? So we exclude negative 6, right? Now we're going to use the second derivative test to determine the maximum values, right? So I have v prime is right here. I need to calculate v double prime. Negative 3.5 s, right? So v double prime of this critical number right here, 6, is negative 3.5 times 6, right? It's going to be negative 9, which is less than 0, right? So by the second derivative test, s equals 6, the volume is maximum, right? And the dimension should be 6, and h right here equals this one, right? 108 minus 36 over 24. It's gonna be 3, right? So finally the dimension is 6 by 6 by 3. Now let's move on to the next one. The guidelines for solving apply minimum and maximum problems. The first step is identify all given quantities and quantities to be determined. If helpful, make a sketch. Step number 2, write a primary equation for the quantity to be maximized or minimized. Step number 3, reduce the primary equation to one having a single independent variable. This may require the use of a secondary equation, which is given, right? Step number 4, determine a feasible domain for your primary equation. Step number 5, determine the desired maximum or minimum value by using the techniques discussed in topic 5.4 and 5.5. Note, this includes taking a derivative, finding critical numbers, and setting up a chart. Alright, now let's take a look at the example number 2. Which points on the graph of y equals 4 minus s squared are closest to the point 0, 2? Alright, so this problem involves minimizing distance, right? Alright, first we need to sketch the graph of this guy, right? So this is gonna be a parabola, right? The y-intercept equals 4, so it could be right here, which is the vertex, right? And then the x-intercept equals plus minus 2, so it could be right here, right? So it's gonna be something like this. Now we need to find a point on the graph which is somewhere right here, s and y, right? And the point 0, 2 right here, such that the distance from here to here is shorted, right? So I'm going to use the distance formula, right? Because we're trying to minimize the distance, right? So that is the primary equation. So the distance formula between 2 points is going to be square root of s minus 0, right? This point is 0, 2. So s minus 0 square plus y minus 2 square, right? Now I'm going to square both sides, so it could be d square equals s square plus y minus 2 altogether squared, right? Now This one is the primary equation, so keep that in mind. The secondary equation is right here. Alright, so from the secondary equation, I need to solve for y and I substitute into the primary equation. So I have d squared equals s squared plus 4 minus s squared minus 2 all together square. I need to simplify this one. So d squared equals s squared. Now 4 minus 2 is going to be 2, right? So this guy turns out to be 2 minus s squared all together square, right? Now I need to take the derivative both sides with respect to s. So it's going to be 2d times d prime equals 2s plus, this one I'm going to use the chain rule, right? So I have 2 times 2 minus s squared times negative 2s, right? Now divide both sides by 2d, right? So I have d prime equals 2s divided by 2, it's going to be s, right? So I have s right here. Now this guy 2 is gone, right? So I have negative 2s times 2 is going to be negative 4s. Negative 2s times negative s squared is going to be positive 2s cubed, right? Over d. But d equal this one right here, right? So it could be square root of s squared plus y minus 2 all together square, right? Now s minus 4s could be negative 3s. Now I need to find critical number, right? So critical numbers e squared d prime equals 0 or undefined, right? So negative 3s plus 2s cubed equals 0, right? Now I need to factor s out, so I have s times 2s squared minus 3 equals 0. So I have s equals 0, s equals plus and minus root 6 over 2, right? And second one, d prime is undefined when denominator equals 0, but denominator cannot be equal 0, right? So we just ignore it. Now we need to use the side charts, right? So I need to draw the number line right here. Negative root 6 over 2. This one root 6 over 2, and it's gonna be 0 right here, right? Now right here we have a 0, 0, and 0. Now I need to test the interval, right? So I'm gonna pick a number within any interval, right? So I'm gonna pick a number 1 right here. Then I substitute 1 for s into d prime right here. Now I need to check the sign, right? So I have negative 3 plus 2 over the bottom always positive, right? So I don't need to worry about the bottom. So the top equals negative 1, which is negative, right? So this guy is negative. And I keep changing the sign. This one is positive, this one is positive, and this one is negative, right? F prime is negative, this one is decreasing, increasing, decreasing, and increasing. The minimum is right here and right here, right? Now you need to conclude that the minimum values occur at s equal plus and minus root 6 over 2 because f prime changes sign from negative to positive at these 2 points. Now you need to find the coordinate of these 2 points, right? So you need to substitute s equal plus and minus root 6 over 2 back to the equation right here to solve for y, right? So I have y equals 4 minus s squared, right? So it's gonna be 4 minus plus and minus root 6 over 2 squared. So it's gonna be 4 minus 6 over 4, right? So it's gonna be 10 over 4, and simplify it's gonna be 5 over 2, right? So you have 2 points, it's gonna be negative root 6 over 2, comma 5 over 2. The second one, root 6 over 2, 5 over 2. And this one is the final answer. Now let's move on to example number 3. A rectangular page contains 24 square inches of print. Alright, so this one is the secondary equation, right? Because it's given. The margins at the top and the bottom of the page are to be 1½ inches. And the margins of the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Right, so this one is the primary equation, right? Now, it involves the area of the page, right? So we know that the distance from here to here is y, which is right here. The distance from here to here is s, which is right here, right? And then we have the secondary equation is s times y equals 24, right? Now the primary equation is the area of the page right here. It's going to be y plus 2, right? The left margin is 1, the right margin is 2, so y plus 2, right? And the top is 1/2, the bottom is 1/2, total is 3, so s plus 3, right? Times s plus 3, right? And this one is the area. Now from the first equation right here, I need to solve for y, right? So y for 24 over s. Substitute this guy into the second equation right here, so a equals 24 over s plus 2 times s plus 3, right? Now I need to multiply this one out, so this guy turns out to be 24 plus 72 over s. Now 72 over s, can I write this one as s power of -1 so that I can take derivative easily, right? Now 2 times s, it could be 2s, right? And 2 times 3, it could be 6 and 24, it could be 30, right? Now I need to take the first derivative, right? So I have a prime, it's going to be -72 s raised to the -2, right? Plus 2, right? And then I will write this one as a fraction, it's going to be -72 over s squared plus 2. Now I need to let this one equal 0 so that I can find the critical number, right? So then 2s squared equals 72, and then s equals plus and minus 6, right? I only pick s equals 6, right? Because the dimension of the page always positive, right? Now the critical number occurs when a prime is undefined, right? So a prime is undefined when s squared right here equals 0, right? But you know that the dimension cannot be equal to 0, right? So there is no value of s, right? Now I need to use the second derivative test to test for the minimum value, right? So I have a double prime equals 144 over s cubed, right? So then a double prime of 6 is going to be 144 over 6 cubed. It's going to be greater than 0. It tells us that the function obtains a minimum value, right? By the second derivative test. You have s equals 6, you need to solve for y, right? So I have the formula right here. So y equals 4, right? Now you need to answer the question, what should the dimension of the page be so that the least amount of paper is used? Which means they're gonna ask you to find the whole thing right here, right? It's not just s and y, it's right here. So you need to add 2 to y and 3 to s, right? So finally it's gonna be plus 3, it's gonna be 9, right? Plus 2, it's gonna be 6, right? So the dimension should be 9 by 6, right? This one is the final answer. Now let's move on to example number 4, optimization on a closed interval. Now let's move on to the next one, optimization on a closed interval. Example number 4. Two poles, one 12 feet high, this one right here, 12 feet high, right? And the other 28 feet high, this one right here, 28. Stand 30 feet apart, so the distance from here to here is 30 feet. They are to be steady by two wires, right? The first wire right here, the second wire right here, which is y and z, attached to a single stake right here, running from ground level to the top of each post. Where should the stake be placed to use the least wire, right? Which means minimum, right? Use your calculator. Alright, so we need to determine the primary equation and the secondary equation. Alright, so the primary equation is right here, w equals y plus z, right? Now secondary equation is, now I need to use Pythagorean theorem in each right triangle right here to solve for y and z, right? Right here. Alright, so y square equals 12 square plus s square, right? Then y equals square root of 144 plus s square. Now z square equals 28 square plus 30 minus s altogether square, right? Now z equals square root of this one. Now I substitute z and y into the primary equation, so I have w equals, now we're going to bring up the calculator to take derivative of ws, right? So go ahead, store the equation first. You're going to hit w of s, and then hit control and this button right here next to number 9. Okay, so it's going to be square root of 144 plus s square plus, then you hit enter. Alright, now you hit menu, calculus, derivative right here. Okay, check derivative with respect to s, and right here you just type w of s. Hit enter. The answer is right here. Now you need to find the critical number, right? So you're gonna solve the equation w prime of s equals 0, which is this guy right here equals 0, right? So you're gonna hit menu, algebra, solve, right? Then you're gonna copy this one down. Don't forget to define the variable of s, right? Put equal sign and 0. Then put a comma and define the variable s. So hit enter. The answer is 9, right? Now you need to restrict the domain for s value, right? The distance from here to here is 30, right? And distance from here to here is s, right? So s must be greater than 0, less than 30, right? So you have three values of s equals 0, s equals 30, and the critical number s equals 9. Alright, so now I need to evaluate the value of w when s equals 0, right? So I just hit w parenthesis 0 close parenthesis, hit enter. The answer is right here. I want to convert this one to decimal, so I just hit menu, number, convert to decimal, hit enter. The answer is right here. Similarly, I need to find the W of 30. Then hit enter. It's gonna be right here. Again, you need to convert this one to decimal number. Alright, it's gonna be like this. And the last one, s equal 9, right? So W of 9. Hit enter. The answer is 50. Now this one is the least value, right? This 53, 60, and 50. So this one is the least value. Now let's move on to example number 5. Rick wants to make Morty a holiday decoration. Rick has 4 feet of wire that can be used to form a square and or a circle. How much of the wire should Rick use for the square, and how much should he use for the circle to create ornaments with the maximum total enclosed area? Alright, now you need to find the primary equation and secondary equation. Remember, secondary equation is what is given, right? Now the secondary equation is 4s, which is the perimeter of the square, right? Plus perimeter of the circle. It's going to be 2 pi r, and total should be 4, which is this one, right? Now the primary equation should be the area of the square plus the area of the circle, right? So it's going to be A equals. Now from the first equation, you need to solve for r. So r equals 4 minus 4s divided by 2 pi. Now I need to simplify this one, so it could be 2 minus 2s divided by pi. I need to substitute this guy over here, so it could be s squared plus pi times 2 minus 2s over pi all together square, right? Now I need to simplify, so this guy turns out to be s squared plus 4 over pi minus 8 over pi times s plus 4 over pi times s squared, right? Now I need to take derivative of this one, so this guy turns out to be 2s minus 8 over pi plus 8 over pi s, right? Now I need to let the first derivative equal 0, so that I'm going to find the critical number, right? So this guy turns out to be 2s minus 8 over pi plus 8 over pi times s, right? Equals 0. Now s equals 4 over pi plus 4. Now keep in mind the range of the wire is 4 feet, right? So the value of s must be between 0 and 1, right? S equals 0. S equals 4 over pi plus 4. And s equals 1, right? Now I have a equals s equals 0. Substitute 0 for s into the function a right here. Alright, so it's going to be 4 over pi, right? Now s equals 4 over pi plus 4. I substitute over here. I need to use the calculator, right? Now I need to store the equation a of s first, right? So I need to hit a parenthesis, s close parenthesis, control, and this button right here. And then I have s squared plus 4 over pi. Then hit enter. Alright, now you need to calculate a of 4 over pi plus 4. The answer is right here. Now you need to convert this one to decimal number. So you need to hit menu, number, convert to decimal, hit enter. The answer is 0.56. Similarly, you need to calculate a of 1, right? Hit enter, it's gonna be 1, right? I need to convert this one to decimal too, right? So 1.27, right? 1.273. Now observe that the maximum value of error is right here when x equals 0, which means Rick should use all 4/5 of y to make the circle shape decoration in order to maximize the total enclosed error, right? Now let's move on to example number 6. Your job is to design a right circular cylinder so that it will hold 22 cubic inches of soft drinks, right? So this one is given, which is this one is the secondary equation, right? However, you must conserve the amount of aluminum used to make the can by keeping the outer surface area to a minimum, right? So the primary equation is right here. What radius should the can make this happen, right? So you need to write the secondary equation, right, which is the volume of the fluid, right? It's gonna be pi r squared times h equals 22, right? Now the primary equation is the outer surface area. So the surface area equals the area of the two bases plus the area around the figure, right? 2 pi r times the height from here to here, right? And this one is A. Now from the first equation, I need to solve for h equals 22 divided by pi r squared. Substitute this one into the second equation. So I have A equals 2 pi r squared plus 2 pi r times 22 divided by pi r squared, right? Now I need to simplify this guy. Now I need to take derivative of this one, so A prime should be let this one equal to 0, so that I'm going to find the critical number, right? So I have A prime equals 0 equivalent to, I'm going to multiply both sides by r squared, so this guy turns out to be 4 pi r cubed minus 44 equal to 0, right? So r cubed equals 44 divided by 4 pi, right? It's gonna be 11 over pi. Now I'm gonna take cube root both sides, so r equals cube root of 11 over pi. Now I need to take the second derivative, so that I'm going to use the second derivative test to determine the maximum or minimum value, right? So I have a double prime, it's going to be 4 pi plus 88 over r cubed, right? Now I need to find a double prime of this value right here. Cube root of 11 over pi, right? If this guy is positive, then I have the minimum value, right? This guy turns out to be 4 pi plus 88 over r cubed, and then when you cube this one, it turns out to be 11 over pi, right? By the second derivative test, the outer surface area obtains the minimum value at the radius equal cube root of 11 over pi, right? Now let's move on to example number 8. A farmer plants two planes a rectangular parcel adjacent to a river. See figure right here. The parcel must contain 245,000 square meters, and then this one given, right? This is actually the secondary equation, right? So you have s times y equals 245,000, right? In order to provide enough grass for the herd, what dimensions will require the least amount? So we need to find the minimum value, right? Our fencing, if no fencing is needed along the river, so this one we don't need this one, right? Now we just need this guy and this guy, right? So the primary equation is s plus 2y, right? And I call this one is perimeter, right? Now from this equation I need to solve for y. So y equals 245,000 divided by s. Substitute over here, so I have p equal s plus 2 times 245,000 divided by s, right? Then this guy becomes p equals s plus 490,000 over s, right? Now I need to take derivative of this one, so p prime equals 1 minus 490,000 over s squared. I need to let this one equal to 0 to solve for critical number, right? So I have s squared equals 490,000, right? And then take square root both sides, so s actually equals 700, right? I need to eliminate the negative number, right? Because it doesn't make sense, right? Now I'm going to use the second derivative test to check if this one is the minimum or maximum, right? P double prime is going to be 980,000 over s cubed, right? And I need to calculate p double prime of 700. Is always positive, right? When you substitute 700 for s, right? Then this guy tells us that p obtains the minimum value, right? S equals 700, right? This is what we need, right? Now we need to solve for y, right? So we substitute 700 for s back over here. So y equals 245,000 divided by 700. It's going to be 350, right? The dimensions required the least amount of fencing is 700 by 350, right? Now the last one is example number 12. I'm going to leave this one for you to practice. I just provide you with the answer key, right? The answer is a equals r squared. There are two different ways to solve this one. The first way, you can use calculus, like what you just did in previous example. We're going to explore topic 5.12, exploring behaviors of implicit relations. Alright, we're going to talk about the increasing and decreasing behavior of an implicit relation. Consider the following relation, which is an ellipse with center 0, 0. 4x squared plus 9y squared equals 36, or you're going to write this one in standard form. It's going to be x squared over 9 plus y squared over 4 equals 1, which is you're going to divide both sides by 36, right? Now, question A. Use implicit differentiation to show that dy over ds equals negative 4x over 9y. Alright, so from the first equation right here, I'm going to take the derivative both sides with respect to s, right? So I have 8s plus 18y dy over ds, right? Equals 0. So I'm going to solve for dy over ds. It's going to be negative 8s divided by 18y. Divide the top bottom by 2. So it will be negative 4s over 9y, right? So this one has been proved, right? Now, note that dy over ds equals 0 when s equals 0, right? So does that mean negative 4s over 9y equals 0 is the same thing as negative 4s equals 0, and then s equals 0, right? and dy over ds is undefined when y equals 0. Why? Does that mean this guy is undefined when denominator equals 0, right? Does that mean 8y equals 0 and then y equals 0, right? Those places correspond to the vertices of the major and minor axis in the ellipse. Alright, so you see the vertices right here. It's going to be negative 3, 0, right? This guy is 3, 0. This guy is 0, 2. And this guy is 0, negative 2, right? Now we have the horizontal tangent line at this point, right? And you see that the slope of these two horizontal lines is 0, right? Also, you have two vertical tangent lines right here, and their slopes are undefined, right? Now, I'm going to rewrite dy over ds equals negative 4s over 9y, right? In quadrant 1, which is this guy right here, and this guy right here, right? Dy over ds is less than 0. Why? Because within quadrant 1 and quadrant 3, s and y have the same sign, right? Either positive or negative, right? This guy have the same sign. You substitute over here, you still get negative side right here, right? Because if this guy negative, when you divide it, it's going to be positive, right? Or this guy positive, you still get positive, right? So the negative side right here remains unchanged, right? That's why this guy negative, right? It tells us that the relation is decreasing on these two intervals. S greater than 0, less than 3, and y greater than 0, less than 2, which is this guy right here and this guy, right? Or s greater than negative 3, less than 0, which is this guy right here, and negative 2 less than y less than 0, which is this guy right here, right? Now in quadrant 2 and quadrant 4, which is this guy and this guy, s and y have opposite side, right? So either this one positive, this guy negative, or this guy negative, this guy positive, right? So if you multiply or divide these two guys, you always have the negative side, right? You combine negative side with dy over ds equal negative 4s over 9y. Then you always get the positive number, right? So it tells us that the function always increase on these two intervals, right? The interval from negative 3 to 0 for s and 0 to 2 for y, right? This one, right? And the second one, 0 to 3 for s and negative 2 to 0 for y, right? Now we're going to move on to the next one, concavity of an implicit relation. And remember that concavity related to second derivative, right? Remember, at the program of s greater than 0, the function f(x) is concave upward, right? At the program of s less than 0, the function f(x) concave downward, right? Now consider the following relation: 3 times s minus y equals 4 plus 3 cosine y, right? We need to prove this one, right? So we're going to take the derivative both sides with respect to s, right? So it turns out to be 3 minus 3 times dy over ds equals negative 3 sine y dy over dx, right? Now I will move this guy to the right, so I have 3 minus 3 sine y all together times dy over ds equals 3. Divide both sides by this guy, right? So I have dy over ds equals 1 over 1 minus sine y. And this one has been proved, right? Now look at this one, dy over ds cannot be equal to 0, right? So we don't have the horizontal tangent line, right? But dy over ds is undefined when the bottom right here equals 0, right? So 1 minus sine y equals 0, sine y equals 1, right? And we look at the unit circle right here. The y-axis represents the sine function, right? 1 right here. So sine y equals 1 when y equals pi over 2, right? And then because the sine function has the period of 2 pi, so you need to add 2 pi n, where n is an integer, right? If n equals 0, it's going to be right here. If n equals 1, it's go back over here, right? If n equals 2, it still go back over here, right? So the graph has vertical tangent line. Whenever y equals pi over 2 plus 2 pi n, the derivative is positive for all other values of y. Therefore, the relation always increases, right? Now, within this interval right here, negative pi over 2 to pi over 2, the second derivative always positive, the graph of the relation is concave up. Similarly, within this interval, pi over 2 to 3 pi over 2, the second derivative is negative, the graph of the relation is always concave down. Alright, now let's take a look at the first example right here. Let f(s) be a function such that dy over ds equals 3s minus 2y minus 8. If f(s) contains the point 2, negative 1, which of the following best describes the point 2, negative 1 on the graph of y equals f(s), right? Now since the first derivative is given, right? So I just substitute this point over here to find dy over ds, right? It's going to be 3 times 2 minus 2 times negative 1 minus 8, right? It's going to be 0, right? So this one is the critical point, right? Now I need to take the second derivative, right? So I have d squared of y over ds squared. It's going to be 3 minus 2 dy over ds, right? Now I substitute this point right here back over here. So I have, but dy over ds equals this one, right? So it's going to be 3 minus 2 times 3s minus 2y minus 8, right? Now I need to substitute this point over here. So I have 3 minus 2 times 0, right? Because I have this guy over here, right? So it's going to be 3, right? Greater than 0. It tells us that the graph has a relative minimum at this point right here by the second derivative test, right? So the answer is A. Now let's move on to example number 2. The points negative 1, and 1, negative 5 are on the graph of a relation whose derivative is dy over ds equals s squared plus y. Which of the following must be true? We're going to check to see if this one is the point of inflection of local maximum or local minimum, right? So we're going to substitute over here to see if they are critical points, right? So I have dy over ds. Evaluate this one as negative 1, negative 1. It's going to be negative 1 square plus negative 1. It's going to be 0, right? So this point is the critical point, right? Now the second one, dy over ds at 1 negative 5. And it's going to be 1 square minus 5. It's going to be negative 4, which is not equals 0, right? So this one is not a critical point, right? Now, I'm going to check the second derivative, right? So I have d square y over ds square. It's going to be 2s plus dy over ds, right? And I'm going to evaluate this one as the point negative 1, negative 1. I don't need to evaluate this one, right? This one, same thing. I need to put negative 1 and negative 1 here, right? So I have 2 times negative 1, right? Plus dy over ds at this point equals 0 right here, right? Plus 0. So it could be negative 2 less than 0. Now, since the second derivative at the points negative 1 is less than 0, by the second derivative test, this graph has a relative maximum at this point, right? So the answer must be C. Now let's move on to example number 3, concavity of an implicit relation. Consider a curve whose first derivative is defined as dy over ds equals 3 over 3 plus cosine y. Determine the concavity of the curve at the points for which 0 less than y less than pi. Give a reason for your answer. Alright, you need to take the second derivative of this one, right? So I have d square of y over ds square, right? So it's going to be, I'm going to use quotient rule, right? U over v prime is going to be u prime v minus v prime u over v square. Alright, so it's going to be this one derivative equals 0 times this one is going to be 0, right? Minus v prime is going to be plus sine y dy over ds times u, which means 3, right? So I put 3 in the front, over v square, which means 3 plus cosine y all together square, right? Now I'm going to replace dy over ds with this guy. So it turns out to be, so it's going to be 9 sine y over 3 plus cosine y all together cube, right? Now we're going to draw a unit circle. Alright, the x-axis represents the cosine function, right? And the y-axis represents the sine function, right? Now, given the domain 0 to pi, right? Which means upper half circle right here. Alright, now I'm going to split this one into two intervals. Now from 0 to pi over 2, right? Within this interval, sine and cosine always positive, right? So if you substitute over here, the second derivative always positive, right? Now the second interval is going to be from pi over 2 to pi right here. Sine is positive, right? And cosine is negative, right? Now cosine is negative, I substitute over here. You know that cosine y is always between negative 1 and 1. So when you add 3, it's always positive, right? So the bottom is positive, the top is positive, the whole thing is positive. So in general, the second derivative always greater than 0 within this interval, right? And the curve is concave up on this interval, right? Now let's move on to example number 4. Consider the curve defined by x squared minus y squared minus 5xy equals 25. Show that dy over ds equals 2x minus 5y over 5x plus 2y, right? So I'm going to take the derivative of this one. It's going to be 2x minus 2y dy over ds. This one right here, I use the product rule, right? So I have negative 5y minus 5s dy over ds equals 0, right? Now I factor dy over ds out, so I have negative 2y minus 5s times dy over ds, and then I subtract 2s and add 5y both sides, right? So I have 5y minus 2s. Now divide both sides by this guy, so dy over ds equals 5y minus 2s over negative 2y minus 5s. Multiply the top bottom by negative 1, so I have 2s minus 5y over 5s plus 2y. Right, so this one has been proved, right? Now, question B, find the slope of the line tangent to the curve h, each point on the curve when s equal 2. Alright, so when s equal 2, you substitute 2 for s back to original function right here to solve for y, right? So I have 2 square minus y square minus 5 times 2 times y equals 25, right? So I have negative y square minus 10y minus 21 equals 0. Multiply both sides by negative 1, right? So y square plus 10y plus 21 equals 0. Factor this one, so I have y plus 3 times y plus 7 equals 0, right? So y equals negative 3 and y equals negative 7. So you have 2 points, 2 comma negative 3 and 2 comma negative 7, right? Since the question asks you to find the slope, right? So you just substitute this point over here, right? So I have the first slope is going to be dy over ds at 2 comma negative 3. So it's going to be 2s minus 5y, which means 2 times 2 minus 5 times negative 3 over 5s plus 2y, 5 times 2 plus 2 times negative 3, right? So it's going to be 4 plus 15 over 10 minus 6. It's going to be 19 over 4. This one is the first slope. Now the second slope, dy over ds at the point 2 comma negative 7, right? So it turns out to be 2 times 2 minus 5 times negative 7 over 5 times 2 plus 2 times negative 7. It's going to be 4 plus 35 over 10 minus 14, right? So it could be 39 over negative 4 or negative 39 over 4, right? This one is the second one. Now let's move on to question C. Find the positive value of s at which the curve has a vertical tangent line. Alright, so the slope is right here. I need to copy over here. The curve has a vertical tangent line when the slope is undefined, right? The slope is undefined when the denominator right here equals 0, right? So you have 5s plus 2y equals 0. Now I need to solve for y, so y equals negative 5 over 2s, right? I substitute this guy back to the original equation right here. Alright, so I have s squared minus y squared, which means this one squared, so it's going to be 25 over 4s squared. Remember, you have two negative sides right here, right? So when y squared, this one becomes positive, so you still have a negative side right here, minus 5s times negative 5 over 2 s equals 25, right? Now I'm going to simplify this one, so I have s squared minus 25 over 4s squared, right? Plus 25 over 2s s squared equals 25, right? Now I need to multiply both sides by 4. So it's going to be 4s squared minus 25s squared plus 50s squared equals 100, right? It's going to be 29s squared 100. Now s squared equals 100 divided by 29. So s equals plus and minus square root of 100, which means 10 over square root of 29, right? Now radicalize this one, is going to be 10 root 29 over 29, right? Plus and minus. Since the question only wants you to find the positive value of s, right? So the answer must be s equals 10 root 29 over 29, right? Let x and y be functions of time t that are related by the equation s squared minus y squared minus 5sy equals 25. At time t equals 3, the value of s is 5, the value of y is 0, and the value of dy over dt is negative 2. Find the value of ds over dt at time t equals 3. Alright, so we need to take derivative both sides with respect to t, right? So I have 2s ds over dt minus 2y dy over dt minus this one right here. I use the product rule, right? So it's gonna be negative 5 ds over dt times y minus 5s dy over dt equals 0, right? Now I just substitute value. ds over dt is what I need to solve, right? So I have 2 times s equals 5 ds over dt minus 2 y equals 0 times 0 dy over dt equals negative 2 minus 5 times y equals 0 times ds over dt minus 5 times s equals 5 dy over dt equals negative 2 equals 0, right? So this one 0, this one 0, right? So 2 times 5 equals 10, right? So 10 ds over dt. This one right here becomes 50 equals 0. So ds over dt equals negative 5, right? And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young, it is just begun.